We now begin session one. Topic for this session is Introduction to Quantum Computing. Our distinguished speaker for this session is Professor Dr. Pradeep Kumar, a highly respected academic and researcher. He is a distinguished professor in the Department of Computer Science and Applications and director of the IT cell at Kurukshetra University with over 27 years of teaching experience in undergraduate and postgraduate programs. He holds a PhD in computer science and applications, along with MSc degrees in computer science, software and statistics, and operational research. Dr. Kumar specializes in subjects like design and analysis of algorithms, machine learning, programming languages, data structures, and cloud computing. An accomplished academic, he has authored over 80 research papers in SCIE, Scopus, and WOS index journals, published two patents, and guided numerous PhD and MTech students. With extensive involvement in organizing workshops, refresher courses, and conferences, Dr. Kumar has made significant contributions to the academic and professional development of his field. His research interests span optimization, network routing, anonymization, privacy preservation, and sentiment analysis, and he actively participates in institutional roles as a board member, selection committee expert, and resource person. Before we begin, a gentle reminder to all the participants. Kindly keep your microphones muted during the session. Please post your questions in the chat box, which will be addressed during the Q&A session. Without further delay, let us warmly welcome Professor Dr. Pradeep Kumar. Sir, over to you.
Thank you, ma'am. I hope I'm audible to everyone.
Yes, sir.
Fine. Thank you. So I think I can start the proceedings.
Yes, sir.
Right. Thank you, Dr. Pawan. I'll be discussing basics of quantum computing over here. Before starting, let me ask a few questions from the participant, if possible. Whether any of the participant can tell me why quantum computing is needed and what is quantum computing, so that I'm able to know that what you already know about quantum computing and I can proceed accordingly. So if someone can tell me what they are understanding with the quantum computing. If there is anyone, please.
It uses the phenomena of quantum mechanics.
Right. One thing is very clear that basically quantum computing will be based on quantum mechanics. The principles of quantum mechanics will be used. That's for sure. You are very right, ma'am. Someone else, please.
It basically the speed of the processor.
Need of
yes.
high computation at a faster speed has led to the usage of quantum mechanics in computer application.
Right.
So
Very
it
right.
basically uses qubits to solve the
Yes.
complex problems.
Yes, ma'am. You are very right.
It has the principles of superposition and entanglement.
Exactly, ma'am. You are very right. What else?
Superposition helps to store large amount of data, and he
Right.
processes the data in a very nanosecond.
Right, ma'am. Okay. So whatever you have told us, on the basis of that, what we can identify is you have identified number one, it is based on quantum mechanics principles. That's very true. The second thing we have identified that the speed of the system will become very fast. Again, very true. Another thing is that this particular mechanism of quantum computing is based on qubits. Again, very right. Okay. And someone is telling that one of the application in QCA, very right. Okay. Actually, there are a number of applications of the quantum computing, and some of the applications could be actually the whole world changing applications. Okay. If and as and when they are implemented. So in the healthcare, actually it can become a game changer. Okay, so these type of scenarios are there with the help of quantum computing. Okay, so very large amount of computation can be done with the help of quantum computing. Okay, so basically Uh, Suppose I wish to learn quantum computing. Okay, what should I know? As you are telling that there is a principle of superposition. Okay, there is a principle of entanglement. So all these principles are required to be learned before actually going into the field of quantum computing. So what I will be touching upon, I'll be discussing these topics in brief. Okay, so that at least we are having the basic idea of the quantum computing, so that during these 5 days during your workshop you are able to understand actually the detailed quantum computing, what is the basis behind that. Okay, so I will be just focusing on the basic part. I will not be going into the depth part of the quantum computing. Okay, so I'll be sharing my presentation. Give me a minute, please. So I hope it is visible to everyone.
Yes, sir.
Right, right, right. Thank you. Thank you. So basically, first thing is that again, let me ask the person from the persons who are already familiar with quantum computing. What does this indicate? This is a circle, basically. Okay. So what does this circle indicate? If someone can tell me, it will be easier
Block
for me.
sphere. Block
Yeah.
sphere.
Yeah, exactly. So one term that ma'am has told us is a block sphere. Basically, it is a block sphere, although it is appearing like a circle, but still it is termed as block sphere. Okay. What else you know about this picture? Someone else can tell me actually.
To rotate the qubits.
Yes, actually, if we focus on this diagram, let us start from this diagram itself. Okay, there are two terms. One is written as 0, one is written as 1. Okay, and there are some symbols. Okay, these are some symbols. Okay, actually, these symbols are termed as. Can someone tell me what does these indicates? What is this symbol and what is this symbol? If you can speak out that. Okay, otherwise I heard every time I need to go to the chat box.
Brian,
Grounded in excited state.
Theta and psi.
No, I'm asking 0 and 1. Psi is a separate
Ground-
thing, theta is separate
Grounded
thing.
and excited state.
State vector. State vector. To represent the state vector, we use
State
the ket
vector.
and the block
What does this?
notation.
What is the meaning of what is the name of this notation?
Ket vectors. Ket
Okay,
vectors.
exactly. You are very right. Yeah. You are very right. These both of them are termed as ket vector, KET. Okay, there are two type of vectors. One is BRA, other is KET. Okay, if I change the position, if I say this parenthesis over here and then a straight line over here, it will become a bra representation. Now it is actually the representation is ket representation, right? So these are the basis of the representation. These are the basis representation, right? Okay, 0 and 1. Just like in classical computing, we are having 2 bits only, that is 0 and 1. Similar to that, in case of quantum computing, we will be having two fixed values, that is 0 and 1. Although these are not the only values which are available in the quantum computing, there is third thing as well. And third thing, as someone of you told me that there is a concept of superposition. So that is a position of superposition, that is there can be in between values. Okay, it can be either tending towards 0 or it can be tending towards 1. Okay, how to identify that we'll discuss a bit later, right? Okay, so that type of scenario is there with the quantum computing. Actually, we can understand this concept with the help of tossing of a coin. Suppose you are tossing a coin. Okay, one thing is coin has been tossed and it has fall down. Okay, and on the top of that coin there will be either head or tail. Okay, so that is the final answer, that it is either head or tail. That is the final answer, right? Okay, but the thing is, if you wish to know the in between states, okay, in between states are number of in between states could be there, unless until it has fall down either on 1 or 0, there will be some probabilities which will be related to either 0 or 1, and depending on those probabilities we can actually define that whether it will be coming out to be zero or it will be coming out to be one, that is basically the concept of quantum mechanics and quantum computing. Okay, so in case of quantum computing, we are using basically the qubits, which are, you can say, very much similar to classical mechanics, that is 0 and 1. But in between, there is a third thing, that is the superposition principle as well. Okay, and these angles, as you notified, that this is the theta angle, that is the psi angle, and this basically is the representation which is termed as direct notation. Okay, there is a notation which is termed as direct notation. Okay, this is the psi. We'll be considering the formula for that thing. Okay, and this is a three-dimensional representation in terms of x, y, and z axis. Okay, so we'll be discussing all these things and we'll be trying to discuss. I will try to learn from you people, right? Okay, so let us start with that. So what we are saying in the first slide, quantum computing is a science obviously based on quantum mechanics along with information theory, because our basic motive is that we should have fast computing. We are able to store a large amount of data, but the important thing is, till date, if I wish to implement quantum computing, okay, then the storage requirement in case of quantum computing are very large. Okay, and if I wish to maybe perform some calculation using quantum computing, using all the possible superposition, it will actually not be feasible. Okay, so storage is a big problem in case of implementation of quantum computing. Okay, so that's why we need to confine ourselves to the limited storage or the limited states only. We can't go to the infinite states and all those things. Okay, so basically that's what we are trying to say, that it is based on, obviously we wish to store some information. Why we are saying information theory? Because one of the major application of quantum mechanics is, I'm sorry, quantum computing is cryptography. That is, you are able to send the message in such a form that no one, and I can't say no one because hackers are very, you can say, learned person. Okay, and they generally crack the things. Okay, so that type of thing is there, but the data will be much more secured if we have implemented quantum computing as compared to classical computing, right? Okay, so that's why we are saying it is based on information theory and quantum mechanics. Okay, second thing that we are talking about is that if when we go into the structure of quantum computing, it basically defines the universal language to efficiently write quantum algorithms. And in case of quantum computing, we will be writing the algorithms, obviously, which will be termed as quantum algorithms. Okay, there are a number of algorithms for that. For example, one of the very popular algorithm is Shor's algorithm. Some other algorithms are also there. Okay, if we further go into this, quantum algorithms are basically those algorithms that exploit some properties, obviously, which are derived from quantum mechanics, as we have discussed. Okay, in order to work with quantum algorithm, we need to operate through computer which is able to manipulate objects in which quantum component is sufficiently manifest. That means the computers that using nowadays might not be able to handle the quantum algorithms. We will be needing special type of computers which will be termed as quantum computers. Okay, because as I told you that they will require a large amount. Even sometimes such type of calculation might be there. Even supercomputer which are exist in existence nowadays, you will not be able to, even they will not be sufficient enough to handle the quantum computing. Okay, so that type of situation is there with the quantum computing. Okay, so basically such type of computers will be termed as actually quantum computer, which are dealing all with all this. Okay, uh, now a question is whether we should study quantum mechanics first and then only we should shift our attention to the quantum computing. Answer is no. Okay, it is not necessary to learn the quantum mechanics in detail, although the basic knowledge of quantum mechanics will help. Okay, but it is not necessary to be an expert. Okay, to understand the idea, basically, we should know some basic principles. And the first principle as all of you were telling, that it is the superposition principle. Now, let us try to understand the superposition principle, although most of you are familiar, but still, let us discuss that thing as well. Now, if you just focus on this, okay, if you are just focus on this, uh, this is basically, if you try to read this, okay, so what is written over there? If someone can tell me what is written above, the sentence is all right. The sentence which is written over here. Okay. So if someone can tell me.
Alive.
Okay.
Dead or alive, both are white and black.
Actually, it is the combination of dead and alive, right?
Alive
Okay.
and dead.
Yeah, alive and dead or dead and alive, whatever it is. Okay. So basically, if you are focusing on this, if you are focusing just on the black, correspondingly, the answer will be different. If you are just focusing on the white, in that case, the answer will be different. Okay. So that means this state is a mixed mode type of state. Okay. It is not clearly telling that whether we are talking about alive or whether we are talking about the dead. Okay. So this type of state in which we are not sure whether it is alive, whether it is dead. In the picture also, basically the cats are being shown. One cat is, you can say, dead, other cat is alive. Okay, two pictures are being shown. Okay, so for that thing, the situation becomes that if someone is asking what this picture is showing, okay, you just need to answer in a single sentence whether the cat is dead or cat is alive. You can't answer because it is the superposition type of principle. That's why basically this concept is termed as superposition principle, in which you are not able to answer finally that whether it is dead state or alive state. And it is very much similar to tossing of a coin when it is spinning. It has not fall down on any either head or tail. It is still spinning. You will not be able to answer whether it will give you the answer as one or whether it will give you the answer as zero. Okay. But when you apply another principle to the superposition, which is termed as measurement, in case of measurement, what it will do, it will disturb the superposition principle or the superposition state, and it will convert the superposition state, or you can say the superposition state will be collapsed into a classical state. And the classical state, as we are already familiar, are only two possibilities are there, that is 0 and 1. Okay, in this case, dead or alive. Okay, so these type of things are termed as basically measurement. Okay, so the first principle was superposition. The next principle, which is very much related to the superposition, okay, is measurement. Okay, so what we are saying that with the measurement of a quantum value, we mean the process with which through instruments quantify a certain quantity belonging to microscopic object. Okay, now what we mean by this microscopic object, that is with the help of which you are able to identify the final state of the input. Okay, so basically that is the basic idea about the microscopic world. Okay, then the next principle that we can talk upon is quantum entanglement. Okay, now what we mean by entanglement. Okay, if someone can tell me again what is entanglement, if you are familiar with that. Okay, so
If
let me
we know
discuss that.
one
Yeah,
state, we
please.
can able to determine the another state.
Right, exactly. Okay. Uh, so if someone is sitting in front of me, suppose, okay, and I am doing something, and correspondingly there is some reaction. Okay, I am performing something, okay, or I am doing something, correspondingly that person is able to react accordingly. Okay, so that is a type of entanglement. That is, there is a reaction depending on whatever I am doing. Okay, but in this case, the distance is very less. That is, both are viewing each other. Okay, but in case of quantum entanglement, what we are saying, that whatever may be the distance, for example, if a thing is happening today, okay, and if you are looking upon maybe after 30 years, okay, if the effect of this moment is still shown on that particular event which is going to take place after 30 years, or if there was an event which was occurring 30 years earlier and the effect of that moment is still on this particular moment, that is termed as entanglement. Okay, so that means when one thing, or you can say one particle, it may be particle or whatever it is, if it is affecting the other, okay, so that becomes the entanglement. In simple words, in layman words, you can say before marriage, okay, the husband wife don't know each other, okay, but after marriage there is an entanglement, okay, that means there is a reaction basically, okay, so they might behave similarly, or these type of examples can be quoted upon for discussing the quantum entanglement, okay. The distance was very far away, but still they are behaving in the same manner or something like that, so that becomes basically the basic idea of entanglement, okay. It is not necessary that both are behaving in the same direction or both the objects are doing the same thing. It may be opposite also. Okay. But still they are related. Okay. So that means if one thing is moving, other is moving maybe in another direction, opposite direction, still there is a relationship. Okay. So that means there will be some relationship that is termed as quantum entanglement. Okay. So that means the two particles, the two quantum particles are binded by quantum entanglement. Okay, so that is another principle, right? Then there is another principle that is termed as tunneling effect. Okay, now let us try to understand what we mean by tunneling effect. Okay, so if we try to discuss the tunneling effect is simple. It can be understood just by this diagram. Okay, and just look at this in the classical physics. Okay, suppose you throw a ball. Okay, or a person is going with the ball. Okay, and he's trying to throw the ball, and ball will come back. Okay, so that is bouncing ball type of principle is there. Okay, but if this is the scenario, okay, if it is quantum physics, okay, it might come back or it might go through this wall. Okay, so in quantum physics, it might be the case that this ball has gone through the wall as well. Okay, so this effect actually is termed as tunneling effect. That is, when a particle manages to make a transition that is not normally principal as per the rules of classical mechanics, it is only possible as per the principles of quantum mechanics. So quantum particle basically can cross energy barriers. Okay, so that type of scenario is there, that so much energy is there. Actually, why there is so much energy is because in quantum mechanics there is the impact of, basically we are studying the impact of electrons, photons, these type of things are being understood, or these type of things are being implemented in the quantum computing. Okay, and a lot of energy when electrons are flowing, or these type of things are there, lot of energy is there, so corresponding to this tunneling effect is there. Okay, so basically these are the three basic principles which will be used in the quantum computing. Out of these, tunneling effect we might not be using as such, okay, but we'll be using superposition principle, we'll be using measurement principle, and we'll be using it up to some extent quantum entanglement as well, right? Okay, now this is just historical type of thing in this slide. This is telling about the quantum mechanics, what quantum mechanics has done. Okay, so basically these are some of the, you can say, invention of the quantum mechanics, that is laser light or transistor or GPS or touch screen. These are some of them. Okay. Uh, uh, so there are a number of examples. So basically the basic idea of the quantum mechanics is that quantum mechanics is used, basically every research is being used for the human betterment. Okay, and same is the case in case of quantum mechanics. Quantum mechanics is also doing the same thing. So these are the things, obviously with the help of which our lives has become easier. Okay, basically historically, if we talk about quantum physics or quantum mechanics, there are two phases, or you can say two exploitation, or two, you can say, it was originated in two different manners. Okay, so quantum revolution, you can say two revolutions were there. First revolution occurred between 1960 to 70. Okay, and in this case, these some of the devices were invented. Okay, uh, in the first quantum, which was between 60 to 70, the basic idea was we were able to exploit quantum mechanics to dominate the behavior of system of atoms. Okay, so at that point of time, we were talking about system of atoms, that lot of atoms are producing a lot of energy and these type of things. That is a collection of number of atoms we were talking about. But in the second quantum revolution, the key concept has been changed. Now the thing remains same. We are able to exploit in both the cases. We are exploiting quantum mechanics. In the earlier phase, we were discussing the domination of the behavior of system of atoms, but now we are trying to dominate the behavior of a single quantum object. Okay, so that means we are now focusing on a single quantum object. And if we are able to understand the concept of single quantum object, we'll be able to understand and we'll be able to exploit basically the system of atoms in much more better way. Okay, and this is the basic diagram that is in these are the various things with the help of which we are able to learn about the quantum computing, that is with the help of communication, computation. Simulation is a very important tool, because without simulation, we won't be able to understand how the quantum computing is working. So that's a very important tool. Okay, and we can use in sensing or meteorology. So these type of things are there with reference to quantum computing. Okay, so these type of things are there. And when we talk about historical things, one of the he is also known as the father of, you can say, quantum computing. Okay, so basically there was a physicist named as Richard P. Feynman. Okay, and he was actually the first person to think in terms of alternative computer. Okay, which is a bit different from classical computer. Okay, and it is not using classical objects, rather, because we are saying that computer should be very much close to the real life. Okay, so that's why Feynman thought that there should be some quantum behavior shown by the computers as well. Okay, so that's why bits he thought that the bits crossed by the current should be there. Okay, so this is the basic idea that was given by the Feynman. This was a very famous quote of Feynman. Okay, that he said that nature isn't classic. Okay, damn it, if you want to make a simulation of the nature, you would better make it quantum mechanical. That is, you can't make a simulation of the nature just based on the classical system. You will need actually quantum mechanical system. Okay, and it's a wonderful problem, and obviously it's a difficult type of thing. It's not an easy to create a quantum computer. It's not easy to learn the quantum algorithm. So it's a bit typical or a difficult thing till date, right? Uh, So with this particular statement, actually, it was this statement due to which a lot of people were attracted through Feynman. Okay, and they also thought in these terms, that is, quantum computers can be made or quantum computing can be executed. Okay, in addition to that, there are some more scientists. And one is Deutsch, and there is Benioff. Okay, so they are also involved in the concept of quantum computing, right? Okay. Now we come to the basic ingredient of the quantum computing, which is termed as this classical computing. Okay. I'm sorry, qubit. I'm sorry. Okay. Now, when we talk about classical computing, we are already familiar that we are using 0 and 1 concept. Okay. That is, you can say, on and off type of concept is there. Okay. So bit we are already familiar and don't need to discuss this particular thing. So this is the basic logical unit. But when we talk about quantum computing, the basic logical unit of the quantum computing is qubit. Okay. So qubit again is going to represent, the final representation will be in terms of 0 and 1. Okay, just like classical bit, that is, the final value will be either 1 or 0. Okay, but as we discussed that there are number of other states which are termed as superposition states, that is all the states which are lying between 0 and 1. Okay, so from 1 to 0 you are moving in that direction, or from 0 to 1. Okay, so there are number of states. For example, this is the final state, this is the final state, but in between this state could be there, other states could be there. All these states are termed as superposition states. Okay, so basically the qubit final states are two, but in between there is a state which is termed as superposition state. Okay, so basically the qubit, okay, the idea behind is to replace the bit with something that is capable of manifesting evident quantum behavior. First of all, superposition. So that means qubit will be having three different type of thing, two just similar to classical bit 0 and 1. In addition to that, it is also able to support the principle of superposition, that is the states which are lying between 0 and 1, right? So that becomes a qubit, right? Now, if we further go into the qubit, basically qubit, you can say, as we have understood that it is the quantum equivalent of a bit. Okay, qubit can be represented by an atom. Okay, so basically we're talking about a single atom now. Okay, we are not talking about multiple atoms. We are talking just about a single atom. Okay, basically the qubit can be represented either by an atom, or you can say a trapped ion, or by macroscopic object which under particular condition can exhibit quantum behavior. So any of these which are able to exhibit the quantum behavior means that is they are able to go into the classical states as well. In addition to that, they are also able to handle the superposition states. For example, if this is the input 0 and 1, so the measurement, when the measurement is done, the final output, because measurement means you are changing the state to a single classical state. Okay, once the measurement has been applied, you can say forcefully you have converted that into either one state or into zero state, but in between there are 0 or 1 number of superposition states are also there, right? Okay. So on the basis of qubit chosen, determine which state is in the one state. We can identify this using some probabilistic principles. Okay, so that type of thing is there with reference to the qubit. Okay, and qubit will also allow us to take the quantum effect. So we already know that particular thing. Okay, now the question is, how can we manipulate the qubits while taking into account the effects induced by quantum mechanics? Okay, so for this thing to understand, now the question is how the qubit is able to handle the effect that is created by superposition. Okay, and how we can implement it in quantum computing. Okay, so basically what we'll be doing, we'll be using some mathematics. Okay, so mathematical formalism of the quantum mechanics we need to understand for that purpose. Okay, so and after that we'll be studying, if time permits, a bit about computing circuits as well of the classical computation, right? Okay. Now let us take a basic review of quantum computing, and for that purpose we need to know basic, just basic of the linear algebra and quantum mechanics mathematical formalism, right? Okay. So for that purpose, there are some notation which are termed as direct notation. There is a notation, direct notation is there. Okay. So basically this, as you have already seen, this is the representation, which is the cat representation, and this is the bra representation. Okay. And this representation basically is a vector. Okay, of the various values, that is, this is termed as psi 0 to psi n, and similarly rho 0 to rho n. So these are just the representation direct notations. Okay, so these are predefined. We won't be questioning on this because these are the notation given by the quantum computing. Okay. Then we'll be using these type of things in case of quantum computing, that is dot product or inner product. Okay. First we are calculating, that is the basically the bra part and then the ket part. Okay, so bracket, it becomes a bracket, that's why it is termed as bra and ket. Okay, okay, c is missing in this case, it is bra, it is ket, but still it is equivalent to, you can say, bracket. So it is calculated like this, and this notation. Okay, so this is basically termed as the direct notation. Okay, so corresponding to this summation of rho I into psi I, so that is the inner product. We'll be trying to understand these things with the help of some examples later on. Okay. Then there is another product which is termed as tensor product. Inner product is also termed as dot product. Outer product is also termed as tensor product. So this is the reverse of that. That is, you will be considering the ket part of rho and the bra part of psi. So correspondingly, this is the exclusive OR of these things, and this is not in summation part. So this belongs to this direct notation n cross n. Okay, so correspondingly you can identify this. Okay. Then matrix vector multiplication. I hope everyone is familiar with this, so I don't think I need to discuss this particular thing. Okay, so this is the simple example of a matrix multiplication. I hope you are familiar all of you are familiar that how this matrix multiplication is done, right? Then if we talk about tensor product between matrices, this is slightly different. Okay, this is not common. So this is with reference to the linear algebra. So if you are trying to perform that tensor product, you can say the outer product between matrices, it will be like this: A11 multiplied by whole of this, A12 multiplied by whole of this, like this. This will be the answer. Okay. And correspondingly, if you finalize this, it will be A11, B11, A11, B1, B12 likewise. Okay, so it will become basically this 16, I say 4 by 4, 2 by 2 it is there, 4 into 4. So total element received over here will be 16. Okay, so correspondingly, this is the tensor product between the matrices, right? Okay. Then there is another mathematical thing that is available over here, that is the unitary matrix. Okay, now what is a unitary matrix? Basically, unitary matrix can be defined as if it's conjugate transpose. Now, what we mean by conjugate transpose? One is transpose, there is a matrix, you calculate the transpose of that. For example, if this is the matrix, the transpose will be A1, then A21, okay, then A12 and A22. Now, here we are mentioning conjugate transpose. Now, what does this conjugate transpose indicate? That is, in case of this, actually, we were writing this thing, just a minute, we are writing this thing. So this is comprising of all the sample space, that is, it is including complex number as well as real number. So it is comprising of all the possible numbers, that is whether it is real or complex numbers. Okay. So what we are trying to say over here is unitary matrix conjugate transpose indicates, for example, if the matrix is comprising of 1 plus iota, okay, in the conjugate matrix, it will become 1 minus iota. Okay, so that is the conjugate, that plus imaginary values which are plus will be converted into the negation. So that becomes the conjugate, and transpose will be taken into consideration. And if this equation is fulfilled, that is U into U star, U is the original matrix, U star is the conjugate transpose, and it comes out to be I, and similarly this. So in that case, those matrices will be termed as unitary matrix, right? Uh, if we are having unity matrix, then in quantum mechanics, they actually preserve the norms. Okay, so this is how to identify the norms. Okay, so if this is the scenario that this is the case, and multiplied by this, it comes out to be Tz. Okay, so if it is a unitary matrix, so in that case, what will happen? That is norm of x y. Suppose it is coming out to be C, it implies that the norm of T and Z will also come out to be C. Okay, so that is used in quantum mechanics. So if it is a unitary matrix, then only this will be applicable. Similarly, if it is 1, the answer will be 1. If it is 0, it will also be 0, right? Okay, so that was bit about qubit. Okay, if we further talk about qubit in terms of block sphere. Okay, so qubit basically is defined as a ray of block sphere. Okay, and the block sphere is a mathematical object which is defined in terms of C square. Okay, and whose elements on the surface are identified. Now there are two angles, one is the theta, other is the psi. Okay, so correspondingly the block sphere is the elements of the block sphere are identified with the help of these coordinates. These are the coordinates of the basic, you can say, psi, and these are identified as cos theta by 2. And the second element is e raised to power iota multiplied by this angle, whatever is this angle. Okay, and into sine of theta by 2. Okay, so this is basically the block sphere object which is defined in C square. Okay, and the poles, there are two poles, one is the north pole, this is the north pole, and this we termed as the south pole. Okay, the poles of the block sphere represent the classical states which are termed as 0 and 1. Okay, and mm, these are the two states which are represented over here. Okay, by two different vectors in the direct notation. Actually, they were identified like this. Let me show it to you. These things are there. Okay, 0 and 1 is represented like this. You can say this as 0, and you can represent, these are direct notation, right? Now if we wish to analyze the block sphere, okay, so block sphere can't be analyzed using two-dimensional type of things. For that purpose, we can only analyze, if we wish to perform any analysis of the block sphere, it can be done in the real field. because the angle theta can be anything basically. Okay. And similarly, angle this I can be anything. So that's why we can say that we are able to actually analyze the block sphere only in the real world. Okay. So that type of thing is there with the help of block sphere. Okay. Now let us try to understand how all the calculation are done for the direct notation. That is, for example, if we wish to calculate the value of psi, okay, how to calculate the value of the qubits or the psi in case of psi indicates a superposition type of thing. Okay. So if we wish to identify the value on the basis of superposition, how to identify? Okay. Now look at this angle is the theta. Okay. So psi is represented by a vector of alpha and beta, and which is represented as we have seen cos theta by 2 and sin theta by 2. Okay. Now there are two representation. One is the 0, other is the 1. So 0 will be represented by cos 0 by 2, sin 0 by 2, and it will come out to be cos 0, sin will come as 1 0. Similarly, 1 will be represented using an angle of 90 degree. Okay. I'm sorry, 180 degree. So 1 is represented like this. So it will become cos pi by 2, sin pi by 2. So it will come out to be 0 and 1. So 0 will be represented as this representation 1 0, and 1 will be represented as 0 and 1. So this is just the mathematical representation of these notation, that is for 0 and 1. So this is basically a vector representation. Okay. Now these classical states, that is here, just a minute, here we are looking into the classical state 0 and 1. Okay. So these are basically the classical states 0 and 1. Okay. So you can represent it likewise. Okay. Now if we further move, okay, uh, these were the final states, that is 0. If 0 is the final answer, that is the state. If 1 is the final answer, this is the state. But in between there is a superposition. Okay. Now for superposition, psi is represented as alpha multiplied by the 0 state, whatever is the probability. Alpha will be having some value. Okay. We need to identify. Similarly, this is the one state. Okay. And it is multiplied by beta some probability. So it will be dependent. For example, if you are again tossing a coin, okay, if it is flipping, if it is going towards one state, maybe you can say head state. Okay. So the probability of this will be high. Okay. The value of beta will become higher, value of alpha become lower. Okay. If it is tending towards 0, in that case, value of alpha will become higher, value of beta will become lower. Okay. So this is how this is represented in terms of alpha is related to the 0 state, and beta we are adding to the 1 state. So this state basically is termed as superposition state. Okay. Uh, so that is the basic idea. Okay. Now, if you wish to measure a qubit, okay, the thing is we have already understood what is the superposition state, how the 0 state is written mathematically, and similarly how a 1 state is written mathematically. Now we are trying to understand how to measure a qubit. For measuring a qubit, we use the function which is termed as the wave function. Okay. Now, although we can represent basically the wave function mathematically, okay, but if we represent it mathematically, it will be very difficult to observe the state of superposition. Okay. So that's why in quantum computing, okay, what we do is the basic difference between the measurement of a qubit is that it destroys the superposition state. Whenever you are measuring something, so it will actually destroy the superposition state, and it will give you the answer in terms of 1 and 0, because you will be adding some probability to this, you will be adding some value to this. Okay. For example, if you have added a value maybe 0.7 to this, 0.3 to this, so it will be tending towards 0, the final answer will be 0. Okay. So whenever you are trying to measure the superposition state, so this concept is termed as collapsing. Okay. So it will collapse either into the classical state 0 or in the classical state 1. Okay. So these are the probabilities, as I have told you, alpha and beta are the probability. Okay. Now this is defined like this. The probability of psi being 0, okay, is determined as alpha square, and similarly probability of psi being equal to 1 is determined as beta square. So with the condition that the total probability of this thing, because this probability is indicated by alpha square, this is by beta square. So the total, we already know that the sum of all the probabilities while we study probabilities should be 1. So that's what we are saying. Okay. So the value of alpha basically is indicated as cos theta by 2. So correspondingly, it will become cos square theta by 2. And the beta is notated by sine theta by 2. So it will become sine square theta by 2. So it should be equal to 1 for all theta. Okay. So whatever is the theta value, so it should be 1. Okay. So psi is represented as we have already seen earlier. That is psi is represented by cos theta by 2 and sine theta by 2. Okay. Now, if the angle, now we are understanding these things via some examples. Now, let us assume that the theta is pi by 2. Okay. So that means psi is situated over here. So what it will do? It will become pi by 4, sine pi by 4. So it will come out to be square root 2 by 2, or you can say 1 by square root of 2, 1 by square root of 2. Okay. So alpha into 0, beta into 1. Okay. And the probability of alpha being 0, sorry, psi being 0 and probability of psi being 1 is 1 by 2. Both are having 50%. How have we calculated? You have calculated using this formula, because this is alpha square and the value of alpha is coming out to be 1 upon under root 2. If you square it, it will come out to be 1 by 2. And similarly it is. So that's why the probability in both the cases, if this is the scenario when it is pi by 2, quite obvious, because it is the exactly middle state. Okay. Neither 0 nor 1, that the coin is standing. Okay. If the coin is standing in the straight direction, that indicates either it can fall towards 0 or it can fall towards 1. That is, either it can be head or it can be tail. Okay. You can't guarantee because it is standing. Okay. Just depending on various environmental factor, it can either fall on either of the things. That's why the probability here is 50%. Okay. So that is a particular scenario. Now, if the value of theta is 3 pi by 2. Okay. So if we convert this, okay. So in that case, another example is there, cos 3 by 4, and correspondingly the value is coming out to be this 1 by square root 2, this is minus 1 by square root 2. Again, if you calculate, it will still come out to be 50%. Still, the coin is still standing, but in opposite direction. Okay. So that means earlier the coin was standing in this direction. Now it has changed this direction, but still it is standing straight forward. So still the answer will be, there will be the 50% probability of being 1 and there will be 50% probability of being 0. So that type of thing is there. Okay. Now, if we try to discuss basically this 2-qubit system, now this was a little bit about whatever we have discussed till now, that was based on a single qubit. Okay. There are some systems or will require systems which are involving 2 qubits or even more than 2 qubits. Okay. N qubit system might also be there. So that's why initially starting with the single qubit, now we are shifting our attention to the 2-qubit system. So if it is a 2-qubit system, let us assume there are 2 qubits. One is the psi 1, other is the psi 2. Okay. Here psi 1 is having the angle 60 degree and psi 2 is having the angle 120 degree. Okay. So how to represent it for a classical state? Okay. So psi 1 is represented, just what you have done. We have used the angle and correspondingly we have defined psi 1. Similarly, we have defined psi 2. Okay. Now, what we wish to identify over here is what is the probability of obtaining the classical states 0 and 1 after taking a measurement in these cases. Okay. So for that purpose, we'll be calculating the probabilities. Okay. So probability of psi 1 will be calculating for 0. Okay. What we have done, we have squared that up. We have squared that up. So it comes out to be 3 by 4. 3 by 4 is 0.75. So 75% probability of being 0. 1 by 4 0.25, यानी कि that means 25% probability. And similarly over here, so we have identified the probabilities for psi 1 and we have identified the probability for psi 2, right? Okay. Now after this, once we have identified these probabilities, okay, now if these two are independent events, let us assume that these two are independent events, that the two coins are being tossed independently. You can assume this thing. Okay. Now what are the various possibility? What are the various possible outputs? The outputs are both are zeros. One is first is 0, second is 1. Third possibility is first is 1, next is 0, and fourth possibilities are both are 1. So obviously there are four possible states if it was a classical state. Okay. So as per classical state, it will come out to be first is 0, 0. It is coming out to be 18.75. Can someone tell me how can we identify this as 18.75? How this has come? Can someone comment on this? Is there anyone to comment how it is coming out to be 18.75? Okay. Uh, Actually, we have not discussed as yet how it has come to be 18.75. This is the formula. Let me show you the formula. Okay. This is the formula, that is alpha 1 square, alpha 2 square, then alpha square, beta square. So corresponding to this probability is being calculated. That is 0, 0. Okay. Whatever is this value. Okay. And whatever is this value corresponding to the alpha. Okay. You will be calculating this. What is the value? In this case, the value of 0 is coming out to be 0.75. It is coming out to be 0.25. So you will multiply these 0 and 0, 0.75 multiplied by 0.25. So whatever it is coming out to be, it will be 18.75. Similarly, if you are considering 0 and 1, it is 0.75, 0.75 multiply, sorry, 75 multiplied by 75%. So it will come out to be 56.25. Similarly, 25, 25, it will come out to be 6.25. And in the end, if you calculate this 1, 1, so it will be 25 multiplied by 75, same. So in that manner, this has been calculated, right? So now you know these probabilities. Okay. So next thing is you wish to identify the wave function. Okay. Just a minute. I think, yeah, you're asking. Okay. Just a minute. Let me explain this once again. Actually, you can speak out in between because I'm not looking at the chat while going through the PPT. Okay, so you may ask these questions. Just a minute. Let me show it to you. If you multiplied 75% with, this is in case of psi 1, it is coming out to be 75%. In case of psi 2, the value of alpha, this is the value of alpha 1. This is the value of alpha 2. You need to multiply alpha 1 with alpha 2. Okay, 0, 0. Okay, so when you multiply 75 with 25, let me calculate it and let me tell you exactly. I need to calculate as well. Just a minute. Uh, Let me calculate this. 0.75 multiplied by 0.25. So it is coming out to be 18.75. So that's what it is coming out to be. And similarly, if you are multiplying this 0, psi 1 is coming out to be 0, the probability is 75%. In case of psi 2, it is coming out to be 1, 75%. So 75 multiplied by 75, that means 0.75 multiplied by 0.75. So correspondingly, it will come out to be 0.5625. So it will be 56.25%. So I hope it is clear to you now.
Yes, sir. Yes, sir.
Right, right. Thank you. Thank you.
Thank you.
Yeah, please go ahead.
Sir, is there a relation between theta and psi?
Pardon?
Is there any relation between theta and psi? Theta is 60 degree in psi 1 and theta is 120 degree in psi 2.
Okay.
So this theta where psi 1 it is there, it is showing 75%.
Right.
When you're taking psi 2 for 0, you're taking 25%.
Right.
How is this percentage fixed?
Actually, we are not fixing it. We are just taking a random example. We are assuming these two are independent. Okay, they are not related. Initially, we are not assuming. You can take any angle actually.
But then, sir, in that the sum should be add on to 180 degree, right? Because this is also summing up to 180 degree.
Yeah, exactly. You are right. You are right.
So if the theta is less, the percentage is more, is it, sir?
Actually, it depends. Let me explain this thing. Look at this. In this case, the value of theta is 60 degree. Okay, it is more towards 0. So the percentage of 0 will be higher, percentage of 1 will be lesser, right? That is quite obvious. Suppose
yes, sir.
So exactly 75% is the answer due to this reason. Similarly, if you just look at the side 2, in this case, the angle is this. So that means it is more tending towards 1. So that's why the percentage of 1 is 75% over here. I hope this was the question or something different you need to ask.
No. I got it. Is it similar to the confusion matrix, sir, in machine learning?
Yeah, exactly. You can say this thing. Exactly. Same.
Okay, sir. I got it. Thank you.
Right. Okay. So I think we can move ahead. Now, another thing that we are discussing over here is, now the wave function that represent the possible state of is composed of two qubits. We have seen psi 1 and psi 2. is a function of four different terms. These are the four different terms, 0, 0, 0, 1. These are the four different terms. Okay. Now further we are talking about by extracting the square root of the values obtained as, let me show it with the examples. Now, I think, I don't know why it has come. Just a minute. Okay, I don't know. Anyhow, so next thing is we are calculating this with the help of single vector. That's what we are doing by extracting a square root of the values obtained as the probability of obtaining a combination of the classical states. What we can do is we can obtain a description of the wave function related to the system composed of two qubits. That is what we are willing now. We are willing to identify a single value on the basis of two qubits. That is, as we are having some classical bits, okay, in case of two bits are there, so corresponding to the two bits you will be having a single answer. Okay, for example, you are applying to a gate. Okay, suppose AND gate is there and you are applying two inputs, correspondingly some output will be there. Similarly, if you wish to apply the similar type of principle in case of qubits, so how to deal with that, how to identify the probabilities. Okay, now just look at this. What we have done, we have written over here is the format is cat format, and it is showing psi1 multiplied by psi 2, and it is coming out to be for 0 0, although the percentage it is 18.75, but it is showing 0.43. Okay, in this case it is showing 0 and 1, it is showing 0.75, then 0.25, then 0.43. Now the question is from where 43 has come. Now we are having this picture, that is psi 1 psi 2. This is as ma'am told us that this is more or less like a confusion matrix. Okay, just look at this. We are calculating alpha 1 square multiplied by alpha 2 square. Okay, now the psi 1 probability was here. The probability of psi 1, let me check what was the probability. Probability was it was coming out to be 75%, or you can say 0.75. Okay, and the probability of this was 0.25. Okay, so so if I calculate alpha 1 square, let me calculate, give me a minute. Okay, I'm calculating on my calculator. So 0.75 multiplied by 0.75, it is coming out to be 5625. So that is alpha 1 square. Next, I will be calculating alpha 2 square. Now look at this. What is the value of alpha 2? Value of alpha 2 is basically, I think, zero point 0.5. Okay, so that is equal to multiplied by, just a minute, 0.25.
625.
Yeah, just a minute. Just a minute, please. It's coming out to be 0 0. So alpha 1 square is, if you can help me out, please, if you can calculate the square of 0.75. If someone can help me out, you please calculate this value, alpha 1 square multiplied by alpha 2 square. We already know the value
Sir,
of alpha
alpha
1.
1 is 0.5625,
Okay.
0.5625, and alpha 2 is 0.0625.
Okay, and if we calculate alpha 1 multiplied by alpha 2, what it is coming out to be?
0.0351.
No, I repeat my question. It is alpha 1. I'm not saying alpha 1 square into alpha 2 square, just alpha 1 multiplied by alpha 2. 0.75 multiplied by 0.25. What is the answer
Just
coming
a
out?
second, sir. Yeah.
It is
18.75.
0.1875.
0.1875.
It is
Just a minute, please. Okay, I'll be checking this thing out and I'll come back to this. Okay, basically, mm, 1 square. That is all right. Okay, somehow I'm not getting this. Okay, so what has been seen over there is this is the formula. This is the, you can say, confusion matrix. Okay, in this case, psi1 is represented very similar as we have represented. That is alpha 1 of 0 and beta 1 of 1. Okay, now what does this indicate? That is the value that the probability alpha, how much it is close to this depending on the angle. Okay, so correspondingly cos theta and all those values you will be calculating, and similarly beta 1 you will be calculating, and similarly you will be calculating the value of psi 2. Okay, and corresponding to this you will be calculating the probabilities just like these probability that we have evaluated, these probabilities that of psi 1 and psi 2. Okay, so these probability will be evaluated, and finally you will be creating such type of matrix, and this is the formula with the help of which actually these matrices have been this equation has been calculated. Okay, so I don't know where I am missing the things. Okay, but I'm missing. Okay, so I think we can assume this for the time being. We can continue.
Yes, sir.
Yes, sir. Yes,
Right,
sir.
right.
Yes,
Thank
sir.
you.
Yes, sir.
Thank you. Thank you. Thank you. Thank you. Okay. So the next thing is, now if you are having, this was the system for the 2 qubits only. Okay, you can extend the system in case of multi-qubit. Okay, so this is for the 2 qubit. You can extend it for the 3 qubit system as well. The formula will remain the same: alpha 1, alpha 2, alpha 3. Then alpha 1, alpha 2. That means all the possible combinations will be there. Similarly, it can be extended to n qubit system. Okay, so as you are able to see that with the help of qubits, you are able to generate either a single qubit, a system based on single qubit. You are able to generate the system based on 2 qubits, and you are able to generate a system based on multi-qubit system as well. Okay, and all these qubit system may return to a basic state, to classical state, that is 0 and 1. You will be able to find the answer in terms of 0 and 1 over in case of 2 qubit system, in case of 3 qubit system, or in case of n qubit system. Basically, you are able to identify the answer in case of each type of n qubit system. Okay, so that was the basic idea of the n qubit system. Okay, so in general, what we can say is a system with n qubit is completely described by a vector of 2 raised to power n elements. Obviously, it is coming out to be 2 raised to power 2. If there are n qubits, so it will be 2 raised to power n elements, right? Okay, so that was the basic thing. Okay, if you wish to represent the same thing that you are representing this, okay, you can represent it likewise as well. That is the same thing. The n qubit system can be represented in this manner also. That is psi 1, then exclusive OR of psi 2, exclusive OR of this, and this will come out to be like this. Okay, so what is the difference between the previous one and this one? The basic difference is, in this case, this is basically the tensor product. Okay, and this was the dot product. So that is the basic difference between this representation and this representation. You can represent the multi-qubit system either using dot product or the inner product, and in the second way, the wave function can also be represented as the outer product, or you can say the tensor product. In that case, how you are dealing: first you are multiplying psi 1 with psi 2, that is this type of multiplication, then whatever result coming, then with psi 3, and this will continue unless until you have reached to the last qubit system. Okay, so that type of scenario is there in case of qubit system. As you are able to see, this is represented likewise, right? Now, one more thing is there. From this qubit system, you can convert this into, for example, if you say that there is another notation. Okay. there is another notation, that is delta type of notation is there, gamma type of notation is there, and which is notated as alpha 1 multiplied by alpha 2 multiplied by alpha, and that is gamma 1, then gamma 2 likewise. So this can be implied with this, but if gamma is known, if these things are known to us, question is whether we will be able to identify this position. Answer is no. From this, obviously, you can manage this, you can convert this into a single value. You are able to convert this into a single value. But if we are having a single value and we know these vectors, we won't be able to convert it back. Irreversible. This procedure is not reversible. Reverse statement is not true. You are able to convert several qubits in a single qubit, but the vice versa is not possible. That is, the single qubit cannot be divided into multiple qubits. Okay, so that is another property of multi-qubit system. Okay, so that was a bit about qubits, right? Okay, now let me discuss a little bit about the gates which are used in this quantum computing. Okay, I'll be going through this in a bit fast-paced manner. Okay, so this is basically the diagram and implementation of the classical bit manipulation. There are various type of gates are being used over here. One is the inverter, or you can say the NOT gate. Then there is a AND gate. Then there is a OR gate, and then there is exclusive OR gate. So the various type of gates and their manipulation, the coding for that has been shown over here. Okay, so nothing much. I'm not discussing that thing. Okay. So this is the concept of classical, you can say, computer. Okay, in which you are using these three gates generally. Okay, and or not, exclusive or, NAND, NOR. So these are the various type of gates which are being used in the classical computers. Okay, but when we talk about quantum gates, okay, so basically the quantum gates, they are having the operators which are capable of acting on a system of n qubit. Okay, so quantum gates are able to do these type of things. Okay, so for example, if you say this is one representation of matrix, this is another representation of 4 by 4, this is m by m representation. Okay, so m is comprising of 2 raised to power n. So this is just for showing that how many large calculation can be performed with the help of quantum gates. Nothing much. We have not discussed quantum gate as yet. This is just for representation of the matrices that you can handle with the help of quantum gates. Okay, so in order to act as quantum gate, matrices must meet important prerequisite. What are the prerequisite? One of the prerequisite we have already discussed during the starting of this lecture, that it should be a unitary matrix. The matrix that you are dealing with in the quantum gate should be unitary. Unitary means whose conjugate transpose, when you multiply that, should be returned into an identity matrix. Okay, so that is the first part. Okay, then the second thing that is associated with the quantum gates is that the number of input qubits must equal to the number of output qubits. Okay, whatever is the number of input qubits, the number of output qubit should be same. Okay, if we say that it is single qubit is the output, then this will not be treated as the this will not be treated as the quantum gate. Rather, it should have the 2 qubit as the output. Okay, and another important impact is that quantum gates should be reversible. Okay, so this is reversible. How it is, how I can say reversible? As you are able to see, this is just the representation of the quantum gate. Okay, in this case, P here is assumed as the garbage vector, garbage output. Q is the actual output, which is depending on these exclusive OR. Okay, so this is just like exclusive OR. Okay, and important thing is that with the help of Q, you are able to identify the it is possible to make these operation reversible. How will be making reversible? If Actually, with the help of Q, you will be able to reverse, you will be able to get the values of A and B. Okay, so basically we'll be fixing one of the values, and correspondingly it will be you will be getting the answers. Okay, so just look at this. For example, B. Let me explain this. In this case, when the B is 1, okay, when the B is 1, in that case, it will be basically reverting the things. If it is 0, it will be reverted into 1. If it is 1, if it is reverted to 0. In case of 0, nothing will change. 0 will remain as 0, 1 will remain as 1. Okay. And when we are reverting this, reversible matrix is there. In this case, what we are saying, whenever it is 1, okay, it will be again reversing the things. If it is 1, it will be converting 0 to 1. Okay. If it is 1, it will be converting 1 to 0. And if it is 0, it will remain the things as it is. P, whatever is the value P, that will be the value P. Okay. So that's why it is termed as reversible. So with the help of as many inputs, as many outputs, we can make the quantum gate as reversible, right? Okay. These are the various types of gates which are available in quantum computing. One of the important gate and most commonly used gate is a NOT gate. Okay. So what is the basic motive of the NOT gate? That it basically flips the value. If the input is 0, it will convert that into 1. And if it is 1, it will be converting that into this 0. Okay. So this is the input matrix in our case. Okay. This is the X, which is the inverter. Okay. And it will be converting this value into the flipping. Okay. So that means this was the thing with the help of which this was the input which was flipped into 0 and 1. 1 was flipped into 0. Okay. So this is basically the NOT gate, or you can say 0 was converted into 1. Okay. Another thing is there is another example. This is the example of superposition. This was the exact value. That is the classical value 0 was converted into the classical value 1. Now what NOT gate is doing, NOT gate is converting your data into 180-degree angle. Now look at this. This is the input. The output will be exactly 180-degree. Okay. So correspondingly, the output will be identified. Okay. So if alpha beta, because this is not the exact state, this is the state alpha beta, so it will be converting that into beta and alpha. Okay, so that is the NOT gate. Then there is another single qubit quantum gate, that is which is doing the bit flip. Okay, this is representation of the NOT gate in case of quantum computing. Okay, suppose this is the input, the output will be beta in terms of 0 and alpha. That will be initial matrix is alpha 0 beta 1, but it will be flipped from alpha to beta and beta to alpha. That is the scenario. Then there is another gate which is quite important in quantum mechanics, that is Hadamard gate. Okay, what is the basic motive behind Hadamard gate? Hadamard gate basically incorporate the concept of superposition. Okay, normally the gates are used to convert. If the inverter gate is used, it is going to flip the value. Okay, but Hadamard will be giving you the superposition type of value. Just look at this. Okay, uh, in this case, in the earlier case, when we were using inverter, we were using this identity type of matrix. But when you are using Hadamard gate, this is the you can say matrix with the help of which we'll be applying the Hadamard gate. Okay, and when you calculate this, it is coming out to be this. It will be a 90-degree type of change. Just look at this. This is the original data, and it will be converted into 90 degrees. So original 0 value is now converted into a superposition state. Originally the matrix was 1 0, but the output that is coming out to be 1 upon whatever it is, 1 and then 1 upon 2 square root. Okay, so that is the Hadamard gate. Okay, another thing is this scenario, that this is the scenario, and that this is converted into 90-degree. Okay, so again, this was originally into superposition, still it will remain into the superposition depending on the Hadamard gate. Okay, so Hadamard gate basically converting your data into 90-degree, and the NOT is converting your data into 180-degree. Okay, so these are the various type of quantum gates that we generally deal with. That is the X gate, which is flipping the things, bit flips. Then Z gate, that is phase is being flipped. Now what is the difference between the bit flip and phase flip? Just look at this. In this case, actually the bits, that is beta and alpha, has been interchanged. In this case, the symbol has been flipped with, that is beta was plus, now beta has converted into negative negation. Hadamard basically is just converting your original into 90-degree angle is there, superposition type of scenario is there. Then there is another gate, that is T gate. Okay, which is using basically this notation, e raised to power iota pi by 4, and correspondingly the answer is there. So these are the various single qubit quantum gates. Okay, so these are the single bit quantum gates. So if there is any queries up to this point, we can take up, and otherwise I can discuss 2 qubit gates as well. Okay, so we can take up the queries, I think.
Yes, sir. Sir, not a query, just a
Right.
regular question.
Yeah.
That will we be getting this slide and as well as this recording
Yeah,
if
I'll be
possible?
sharing with your organizers, and I think they will be able to share with you.
Thank you, sir. Thank you.
Right, 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 right.
Sir,
So
what type of algebra is using here?
basically, algebra is more or less similar. Linear algebra is being used over here. Basic algebra is linear algebra that we are applying over here.
Do
Eigenvectors
you
and all those things.
do you cover it in this our session later on?
Actually, I doubt that I will be able to cover, although I was having in my slides, but I don't think I'll be able to cover because it will take a lot of time.
Okay, thank you.
And
Yeah.
sir, I also resolved that 0.43, 0.75, and 0.25 stuff
Okay.
in the previous slide. It
Right.
was like,
Let me go to that so
yes,
that
sir.
he can explain. Just a minute. Give me a minute, please.
Yes,
Uh,
sir.
just a minute. Yeah. Yeah.
Yes, sir. In this 0.43, how is it? Because psi 1 belongs to root 3 by 2 and psi
Yeah.
2
Exactly.
belongs
Exactly.
to 1 by 2. So
Yeah.
root 3 by 4 is approximately 0.43, sir.
Okay.
And similarly, 0, 1 will carry upon psi 1 will be root 3 by 2 as well as psi 2 will be root 3 by 2. So 3 by
Okay.
4, that's 0.75.
Right.
Similarly,
Right.
for psi 1, it is 1 by 2. And for psi 2, 0, 1, 0. That's the third point. 1, psi 1, 1 by 2
Right.
multiplied by 1.
Let me show that actually this is the scenario that you are talking
Yes,
about.
sir. Yes, sir. Yes,
This
sir.
was
Yes,
under root 3 by 2,
yes,
and
sir.
corresponding rate is 1 by 2. So corresponding rate is coming out to be those
Yes,
values.
sir. Yes, sir.
Okay.
Yes,
I
sir.
was not considering these value. I was considering only
Yes, sir.
percentage.
It
That's
is,
why the problem created.
yes, sir. So in psi 1, 0, that is root 3 by 2. In psi 2, 0, it is 1
That
by
is 1
2.
by 2.
Yes, sir.
Yeah.
So
So we
psi
can
0,
multiply and
0.
correspondingly we can, you are right. You are right. So it will
Yes,
come out to be, I think, 1.72 or something like that, and
yes,
divide
sir.
by 4. So it will come out to be 4.3 or something.
Yes, sir. Yes, sir. Yes, sir. That's
Right,
how I
right,
could.
right. Okay, 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 okay. So please, everyone note that particular thing. So I skipped or I missed that particular thing. So that's why the answer was not correct. But now the correct answer can be obtained just multiplying the alpha 1 into alpha 2, then alpha 1 multiplied by beta 2 or something like that. So correspondingly, we can identify the values, right? So thank you. Thank you, sir. Okay. So any other query or should I continue with the maybe 2 qubit? I think we are having some time, so we can discuss a bit about 2 qubit gates as well.
Sir, one doubt.
Yeah, please.
Sir, in Hadamard gate,
Yeah,
this one, sir.
yeah,
Uh, previous to this, sir.
yeah.
So
Even before
because
that. Yeah, yeah, go ahead. Go.
here earlier you told that if the arrow is near to 0, then probability that output is 0 is more. If
Okay.
it is near to 1, it is output is 1. Here in the gates the output is either you are observing the final output, not the garbage output, right, sir?
Okay. Yes, yes. I'm doing the same.
So
Basically,
here,
yeah, let me explain first the Hadamard gate, then you can ask the question again. Basically, suppose an inverter gate is there in classical, you can say classical computer. What we are doing, we are inputting 0, it is reverting us 1, right? And if we are applying this NOT gate, okay, it is doing exactly the same thing. That is, we are applying 0 and it is giving us the output 1, okay. Now, Hadamard is giving this thing. Suppose we wish to use Hadamard as an inverter. Okay, question is, can we use it? Yes, we can use it. But the thing is, in that case, what you will be doing, you will be applying two Hadamard gate. That is one, first it will be converting that into this state, that is 90-degree state. That is earlier it was 0. Now it has converted your input into a superposition state that is in between 50-50 type of state. Okay. And then if you once again apply the Hadamard gate, now it will be converting your input that which was superposition into one. Okay. Now you can ask your question.
So, but what will be the probable advantage of doing like this, sir?
Basically, in some scenario, we wish that input should be converted into a superposition state because we wish to identify the various type of states. For example, if we wish to maybe encrypt something, okay, we wish to transmit the data from one place to another place. We don't wish that data should be transmitted as such. Okay, so for encryption purpose, we can use these type of gates. That is just an example. What we have done, we have encrypted, actually the input was 0, but what we have done, we have inserted a Hadamard gate in between. So the input will be converted into a superposition state and the attacker will not be able to understand whether it is 0, whether it is 1, because there are some probability and which will be evaluated by the receiver. So that can be one of the thing.
So it might be like the QPSK and where you have multiple angles representing one data bit like that, does it?
Exactly. So that's why one of the major application of this quantum computing is cryptography.
Okay, sir. Thank you.
Okay. So any other query, please? Okay.
Sir, will you show any simulation of this in
Actually, in my system, I don't have sufficient capacity to simulate all these things. But what I can do is I can arrange a video of simulation. I'm having the video of simulation, but I'll be sharing with the organizer. Then you will be able to see it.
Okay.
I can do that. Right. So I think we should stop here, but because otherwise it will be a very large lecture. Okay. So that's it from my side. So I think the basics of quantum mechanics I was trying to introduce you, and up to some extent I was able to introduce. Okay, I might not be an expert of quantum computing. I tried my best. Okay, but still, if there is anything left, sorry about that. So thank you everyone for this.
Can I ask one more question, sir?
Yeah, go ahead, please. Go ahead.
Thank you, sir. Sir, in any of the probability, if we count only one qubit, that is 0 and 1, so there are 50% of the chance of getting 0 as well as 50% of the chance getting 1.
Right.
But in case of Hadamard, it is 0 plus 1 by root 2 or 0 minus 1 by root 2.
Right.
I was not able to get why is it in that particular physical state. I'm not sure.
Actually, we are calculating the squares of, we are calculating alpha square and beta square. For example, this is the alpha. If you calculate the square of this, so it will come out to be 1 by 2. And the square of this will also come out to be 1 by 2. So that will be exactly 50% of that, but that type of thing.
Okay, so we are just doing the square root of and then adding it up the sum to get the Hadamard, right?
Yeah.
Oh, thank you so much, sir. Thank you.
Okay. So I think I can stop the sharing. Right. So I think let's check. Dr. Pawan is there?
Yes, sir.
Dr. Amit? Yeah. So I think that's it from my side, Dr. Pawan. So thank you.
Kanika, ma'am.
Thank you so much, sir.
Thank you, ma'am. Thank you.
Thank you, everyone, for your active participation in session 1, our special full presentation on Introduction to Quantum Computing. Thank you so much, sir.
Thank you, ma'am.
Dear participants, please remember to fill out the feedback form after each session. The link has been shared in the Zoom chat as well as in the WhatsApp group.
So Dr. Pawan, should I stay or should I leave?
Thank you so much, sir.
Okay, thank you. Thank you, sir. Thank you.
हेलो मैम, कनिका मैम, पवन सर, पवन सर,
Yes, sir.
Yes, sir.
गुड इवनिंग सर. सर लिंक इज नॉट वर्किंग.
Okay, I will check. Participants, now let's take a short 2 minutes
Sir,
break.
it is working.
Participants, please fill out the feedback form as early as possible.
And now let's take a short 2-minute break to recharge and get ready for the next session. Session 2 promises to be equally exciting and enlightening.
या थैंक यू मैम, इट्स वर्किंग.
Yeah, sir, it's working.
Okay, thank you, ma'am.
Definitely to ask more and more questions on this. So question answers would be at the end. Let us start the session, and I'll keep it very simple. And we'll also try to, I'm just trying to just remove this. Yeah. Just for once, tell me, Kanika ma'am, am I audible? Is my voice not breaking? Is it fine?
Yes, sir. Your voice is audible.
Okay.
Yes, sir.
Okay. Thank you. Thank you, Pawan sir, and thank you for giving this opportunity. It's always a wonderful thing to be associated with RKG. RKG has been doing wonderfully since 2000. I have been associated. So it's one of those wonderful colleges in my neighborhood. And I also live in Sanjay Nagar. So I commute from Delhi. So I've been rushing from Jamia Hamza today. So now I'm back home and ready to take it. So let me just start my presentation, sir.
Yes, sir.
And yeah. Sir, please let me know if I'm visible also now.
Yes, sir. Your presentation is visible.
Yeah. Okay, sir. So we are here to have this topic which is on the screen. We'll try to keep it very simple with very good examples that we'll be looking at. We'll also look at where India is right now in this research, where the government is spending 6,000 crore rupees. Where are we spending that? Because by 2047, it's a dream of our Honorable Prime Minister to become the Vishguru. And to become the Vishguru, I think quantum computing will play a very big role. So somewhere down the line, we have also talked about SDG goals and quantum computing, how we are going to achieve those goals also. We are talking about application areas of quantum computing. We're talking about the principles involved. Very simply, because the next 5 days, what you are going to be looking at in this FDP, and this is a very unique FDP designed by RKG, and I think it's going to be having wonderful contents. And second day, it will have quantum gate based VRP model where we are going to talk about logic gates today, the quantum gates today, and then you will see the implementation on day 3. In form, there is a lab session on day 3 on Qiskit. So Qiskit is one of those Python platforms where you will be programming. So you'll get to learn a lot from this workshop, from this FDP. Let me tell you, and this is really going to be a landmark FDP for your people who want to start, students who want to start the research in quantum artificial intelligence framework. So, Qiskit, you're learning on one day you are learning large language models, LLM, because cybersecurity is a big issue. You're having a session on quantum computing for cybersecurity. You're talking about cryptography, how quantum can break those cryptic codes that we are using. The banks are worried about it, the defense systems are worried about it, but somewhere down the line, we have to learn it. Otherwise, any other country can attack us digitally. So, this is the reason why we are having so many conferences, so many workshops, and so many FDPs on this current topic, quantum computing. So we are having a session on quantum computing for cybersecurity. We are having a session on machine learning and the amalgamation of quantum and machine learning. So this is going to be a wonderful 6 days. Today's session, you will get familiar with this topic, and by tomorrow, you will start to have the Python impact also. So mostly we are going to be programming in Python. I'll give you the idea about Python also, which frameworks are we using, which libraries we are using. So it's going to be interesting session, and rest assured, please wait till the end, and then we will have the question answer session. So quantum computing, it is the future of computation, harnessing quantum mechanics for exponential speed up. So those who are from physics, they understand the topic of quantum mechanics, quantum physics. So this is where those people will be really very happy, those who have done physics somewhere in graduation. So let me take just one example. There is a quote here. If classical computers are like reading every book in a library one by one, so this is the basic difference between your classical programming, classical computing. If classical computers are like reading every book in a library one by one, quantum computers are like opening all the books at once. So you can just assume there are thousands and thousands of books, and if you can open them at once, this is going to be the topic of the day. We are going to talk about superposition. We are going to talk about entanglement. By now, you must have understood that also, because the first session was also on the introduction part of it. So we are taking it further, and we are going to be taking it further very in simple terms, very simple words. So somewhere, anywhere, if my voice breaks up, you can all the coordinator can always just ping, just come on the mic and tell me. So what is quantum computing? Quantum computing isn't just science fiction anymore. Now, this is not just a fiction anymore. It's a technology that could reshape cryptography. We are all working on cryptography, RSA algorithms, and all. So it's a danger that if quantum computing is going to gain popularity, it can break into any code of RSA code. So reshaping cryptography, drug discovery, we are going to be talking about genomic data today and see how with Python, we can use quantum computing, and you are using the Jupyter framework, or you're using Google Colab. So we will have some code also somewhere down the line. So it's a technology that could reshape cryptography, drug discovery, and even how we understand the universe, because quantum mechanics, quantum physics is very close to the universe, because we are talking about electrons, we are talking about photons, we are talking about the electromagnetic force. So this quantum computing is very close to that. So in classical computing, what do we do? Traditional computers that we are using right now, they use bits, and bits, binary digits that exist in one of the two states, 0 or 1. So either the bit can be in 0 state or 1 state. They process information sequentially, following binary logic to solve problems step by step. This is what we have been doing, the binary logic and solving the steps in an algorithmic form. So what quantum computing, on the other hand, uses, there is a new word here. And this word will be used throughout the 90 minutes of the session today. And throughout the 5 days, remaining days, they will be talking about qubits. So quantum computers will be using qubits. We'll see what qubits are that can exist as a 0 or 1 or both simultaneously. And this is going to be tricky to explain on paper. We'll take very good examples of this, and we'll say that the quantum bit qubits are in superposition kind of thing, a topic which is the basic, the principle. So we'll talk on that. So they leverage superposition and entanglement to explore multiple solutions at once. So if we can solve multiple solution at once, as I said, reading all the books at once. So this is going to be the start definition for quantum computing. So three pillars of quantum computing, quantum mechanics, quantum computing. By now, in the first session, you must have gone through superposition. Qubit exists in multiple states simultaneously, enabling parallel processing of vast solution spaces. This quantum property allows exploration of countless possibilities at once. We'll take some examples, and then you'll understand how can my qubit be in any of the states, 0 or 1, or any state in between. We'll talk about that with examples. So entanglement is another pillar of it. This is another principle of it. So qubits become intrinsic connected, where the states of one instantly affects the other. That means two entities getting entangled into each other. This creates a powerful correlation that a classical system cannot replicate. And even if they say, even if you go to another universe, those two qubits would be remain connected. We'll look at that with example. We look at that with Python code also. Then a third important pillar of computing would be quantum gates. We are all comfortable with digital gates that we have been reading, logic gates, NAND gates, NOR gate, AND gate, NOR, OR gate, and there's so many logic gates. But here, there are two, three very important gates which we'll be using in our coding. I'll look at the coding also, and you'll explain how can we do that using a Python code. So quantum gates, specialized operations, manipulate qubits through header mode. This is one of the gates, header mode. This header mode gate, when you will see, and day three, when you do the coding part, the professor who will be doing that, he'll be using this header mode gate, he'll be using the C naught gate, and there you will find that header mode will take your qubit in from one position to another position. So that means it will put it in a superposition. So we'll see exactly, we'll do the programming also. So this FDP you would see is wonderfully planned so that whatever theory you read on day one is implemented right from day two. You start implementing with Python. I'll tell you the libraries, Python libraries that we are going to use, and so on, how we'll start at Google Colab. So when we move ahead, transformative applications that we are talking about. There's one more quote here. Classical computers struggle with problems that grow exponentially, like simulating molecules or optimizing complex systems. Quantum computing offers a fundamentally new way to process information. So this is one of the topic that is there, that is on quantum process information. You have one of the sessions on day 5, I suppose. So you're going to be talking about these transformative applications again on that day. So the revolution, cryptography revolution, this is one thing that is really everyone is worried about it, because if this is going to work, it can break into any cryptography code, it can break into any of the systems, defense systems, banking systems, healthcare systems, and create a havoc. So cryptography revolution, quantum computers can break RSA encryption, but can also break unbreakable quantum key distribution protocols, which we have always said are safe, fundamentally transforming cybersecurity. So cybersecurity again would be under threat, and that is why we are having a session on day 4 of day 5 on cybersecurity, quantum computing for cybersecurity. What are the solutions? How we are going to solve them through Python and the Python quantum AI frameworks like QSVM. We are going to talk about QNN, that is a quantum neural networks. We're going to talk about quantum enhanced reinforcement learning, which is being used in healthcare, finance, logistics, where we are talking about route optimization and fuel reduction. So a lot of things we have to discuss, and we'll cover it up very quickly also in between. So cryptography revolution, optimization breakthroughs, solve logistics, financial modeling, and resource allocation problems that would take classical computers centuries to complete. So even the fastest of supercomputers cannot match the speed what the quantum computing will give you. And the breakthroughs we'll talk about just in the next 4, 5 slides, we'll talk at various companies of IBM and Google. We'll talk about Google Quantum AI Lab, which we can use. So you can write your code and not only run the simulation in Google Colab or Jupyter, you can also submit your job to the Google Quantum AI Lab. You can log in there, make a login ID over there with a password, and then you can submit your work. And then you will get, as soon as it is done, you'll get a mail that your work has been completed. So now you can look at your output. So we'll discuss on that. So cryptography revolution, optimization breakthroughs, as I said, logistics. So logistics is one of those things where quantum computing is really going to break free on route optimization, which will give us the shortest path in a better way, and fuel reduction. So it's going to solve logistics, financial modeling, resource allocation problems that would take classical computers centuries to complete. And then the third application, which we'll see, it is there in one of your sessions, quantum simulation. So when we are doing Qiskit, we will be talking about quantum simulation, the code for quantum simulation, just 10, 15, 20 lines of source code. And you will see you are able to simulate the quantum environment. So it will model quantum systems and chemical reactions with unprecedented accuracy. There would be accuracy accelerating drug discovery and material science research. So this is where healthcare is really going to benefit through accelerating the drug discovery. We understand India was the first country to develop vaccine. So similarly, we use quantum in our healthcare. Definitely in material science research, we are going to get the edge over the world. And as the dream of Honorable Prime Minister says, 2047, we have to become the wish crew. So this is going to be one of those converging technology that will really help us quantum AI framework. So I'll just put it on. So there are a few overcoming critical challenges we'll discuss during the next 5 days. You're going to talk about these things very often. And there's a lot of research going on this. Qubit stability, decoherence causes qubits to lose their quantum properties within microseconds. Maintaining coherence requires near absolute zero temperatures. So you will see we'll have to keep this temperature, near absolute zero temperature, and isolation from environmental noise. So we are going to look at that with example and through the code also. Error correction. Quantum states are fragile and prone to errors. Sophisticated error correction codes require multiple physical qubits to create one reliable logical qubit. We are going to talk about next 5 days. We'll definitely be talking about qubit stability. We're going to talk about the code for error correction, and then the scalability. Building systems with thousands of stable, interconnected qubits remain a formidable engineering challenge requiring breakthroughs in hardware and control system. So still a research is going on. We are in a developing state. India is really getting worked up. We are really working hard to get into the groove of it so that we can compete with the best in the world. So these are the three challenges on which this FDP would rest upon. Qubit stability, we'll talk about it, just talk about it. There would be three types of qubits and how we are going to achieve the stability. Then error correction. There's the algorithms that are there for this. We'll be talking about it, and scalability, we'll talk about it. So there are three groundbreaking quantum algorithms, and somewhere down the line in everyday sessions, you will be coming across three names. We'll be discussing that in detail. So three algorithms are very important. The Shor's algorithm. Shor's algorithm is going to factor large number exponentially faster than the classical algorithm, threatening current encryption standards. It reduces factoring from years to hours. So the hacksters and the pranksters, they were taking years to, they were trying very hard to break into the system. But now, if they get the access of quantum computing, if they're using the quantum computing techniques, definitely they would be able to do it. So Shor's algorithm, we are going to discuss during those 5 days, definitely in Cascade, you're going to develop this Shor's algorithm. 10, 12 lines of source code. Then Grover's algorithm, the name as this is Indian scientist. Grover's algorithm searches unsorted databases with quadratic speed up, finds target items in root n steps instead of the n steps. So definitely just understand, if you Classically, we were taking n steps. With Grover's algorithm, we are taking just root n steps, revolutionizing the search operation. So Grover's algorithm will be used for searching large data sets of data. We'll be talking about it, the framework that we'll be using. We'll be discussing. The third one is Deuce-Joss algorithm. It determines whether a function is constant or balanced with a single query, demonstrating quantum computing fundamental advantage in specific problem classes. We'll see which classes are there where we can apply this Deuce-Joss algorithm also. So these three algorithms, they are the groundbreaking algorithms as far as quantum computing is concerned. So somewhere down the line, we'll be covering this also. Shor's algorithm in Qiskit, we'll be developing this. Grover's algorithm, we'll be developing. So as I said, this is a developing field, and we are working on it. There's a lot of research going on into quantum computing. So there are diverse hardware approaches, qubits. These are types of qubits that are under research and being used by the companies. And this is where IBM and Google has gained the advantage. Superconducting qubits. So this is one of the types of qubits. Superconducting qubits, IBM and Google leads with circuits cooled to near absolute zero. So offers fast gate operations. So Hadamard and CNOT gate, the operations are really fast and precise control. Currently the most mature technology. So superconducting qubits are really being used. They're very popular now. They're being used by IBM and Google. As I said, Google has their own lab. And if you happen to sit on YouTube, you can just type, I want to visit Google Quantum AI Lab, and there are videos. They will take you inside that, and then they will explain what are they doing and what is the technology, what is the direction. So it's a wonderful PP presentations are there which you can look into. So another diverse approach is trapped ion systems. So IonQ is the name of the company. It uses individual atoms held by electromagnetic fields. So they are making use of electromagnetic fields. Those, as I said, those who are from physics background will really love it. So IonQ uses individual atoms held by electromagnetic fields, provides long coherence time, and high fidelity operations with excellent connectivity. So this is a slightly better in terms of coherence. The first one there, he said that the coherence was bad. So we'll be discussing this with examples and see how we are as Indian, we are dealing this. We'll just come up with the more on this. Then third type of qubits, which are under research. Microsoft is doing the research on. Microsoft pursues inherently error resistant. As I said, there is a topic error control. So these are error resistant qubits using exotic quantum states, still experimental, but promises built-in tolerance. So they are going to be talking about topological qubits. Somewhere we are moving in the slides. We'll see. We'll talk a lot more on these topics. So quantum versus classical, as the discussion started, the speed revolution is there, exponential speed up. For certain problems, quantum computers achieve exponential acceleration. Tasks requiring billions of years typically can complete in hours quantumly. So 10K times the potential speed up for optimization problems. Quantum parallelism is again a word. While classical computers test solutions sequentially, quantum systems explore all possibilities simultaneously through superposition. So this was the first thing that we started. The second slide started with the principle of superposition. So superposition is something which you will achieve through your gate. So the professor will also demonstrate that you can achieve the position of superposition through the Hadamard gate. So we'll be discussing in our session also. So while classical computers test solutions sequentially, quantum systems explore all possible simultaneously through superposition, fundamentally changing problem-solving approaches. So we can have a lot to be that we are desiring from this system. So this is the current state. NISQ, here it is here, noisy intermediate scale quantum computers. So Google's 53 qubit. So 2019, quantum supremacy, how it started, 2019. Google came up with a 53 qubit qubit system processor called Sycamore. Sycamore. Sycamore processor completed a calculation in 200 seconds that would take classical supercomputers 10,000 years to complete. So Google came up with 2019, it came up with a 53 qubit processor called Sycamore. Then 2020 to 23, in the middle one, you see the bottom part of it. Uh, there was some disturbance. Hope I'll just ask the coordinator if I am audible and visible both. Please, if you can help me, if I'm audible and visible both. Even a thumbs up from your side can
Yes,
say
sir.
it all.
Yes, sir. You
Yeah.
are audible and
Yes,
visible.
sir. Yes, sir.
Yes,
Okay.
sir.
Okay. Okay. Thank you. So 2020 to 23 was very important. This was a time of NISQ development. Noisy intermediate scale quantum computers emerged with 50 to 1,000 qubits. So you will see as we talk about solutions and different solutions, better solutions, you'll see the qubits will keep on increasing. So now by 2023, they were able to achieve 1,000 qubits also. We'll see what India has achieved also in very 2, 3 slides more. Then we'll get into the Indian scenario also. So noisy intermediate scale quantum computers emerged with 50 to 1,000 qubits, limited by noise. As I said, noise, we have to keep them alone. We'll be discussing more of that, but useful for specific applications. Then 2024, this is the time when things started looking up. Cloud-based quantum computing services expanded. Companies started exploring practical applications despite hardware limitations. We'll see. I'll also talk about the different kinds of books that we have to read for quantum computing. There are 7, 8 very good books that I have read in my discussion. So I'll discuss that also. I'll discuss the research topics also, the kind of research that is going on in IITs and in the TIFF and different institutes of India, and the kind of research that we are doing on quantum AI frameworks and error correction. So we'll talk of that also. So this is the current state and ISQ year era. So quantum future awaits. Achieving a practical speed up in optimization, machine learning, and drug discovery within 3 to 5 years as hardware improves. We are working on that. There's a lot of research going on. And as we'll see just now, our country has invested 6,000 crore on this because we want to become the wish crew. We want to be the best in the world. So quantum advantage, then error correction is what we are really working on, developing fault tolerant quantum computers with logical qubits that can run long complex algorithms reliably. And still we are working, and it may take 5 to 10 years, but we should be able to work on that because our students are working, researchers from IIT, they are working on hybrid quantum classical algorithms now. There's one algorithm, VQE, which is variational quantum eigensolver, which already a lot of research. So I'll keep on talking about the research topics. At the end, I will also summarize them so that you can guide your research scholars, those who are working under you, about these prospects and how they can work on that. So we'll come on that. Long term, universal quantum computing, building large scale fully error-corrected quantum computers capable of transforming cryptography, AI, and scientific discovery within 10 to 20 years. So quantum revolution is underway. While challenges remain, the potential is to solve previously impossible problems, making this one of the most exciting frontiers in technology. So we'll talk about this. Now, we'll talk about the Indian scenario. So just a moment, I'll just have a water, just a sip of water. So if you see Indian's quantum leap, we are going to talk about, and we'll see how we are moving as far as our proud nation is concerned on this. So remarkable milestones in quantum computing. 2023 was a time which is really things are looking up for India now. TIFR unveils India's first indigenous 7-qubit quantum computer, marking a historic achievement in homegrown quantum technology. So, homegrown, this is the part, this is important. 7-qubit quantum computer by TIFR TIFR. Then 2024 testing and validation, DRDO and TIFR successfully demonstrated a 6-qubit quantum processor validating critical quantum computing capabilities and algorithms. So the algorithms which we will talk about and we have been talking about, they were successfully implemented in 2024. And 2025 is scaling up. QPI AI launches India's most advanced 25-bit quantum computer. So we are looking towards 25 qubit quantum computer. We are also working on 50 qubit. We are also working on 100 qubit quantum, but they are all in research areas right now. So we are scaling up gradually, slowly. We are moving ahead. QPI AI is a company launching India's most advanced 25 qubit quantum computer, representing a quantum leap in computational power and accessibility for researchers. Please don't draw anything on the screen, my request, because these are sessions are being recorded. By mistake, it happens sometimes. Please. So National Quantum Mission. So this is acting as a mission here, fueling innovation. So this is where I was saying massive investment. Government of India has committed 6,000 crores from 2023 to 2031, one of the most ambitious quantum programs globally. Strategic focus areas would be we will be working on quantum computing hardware and software. So, as I said, the role of these FDPs and workshops and Atal FDPs is helping tremendously the country tremendously. This is really going to give insights into what we are doing, how we can achieve, and how today we'll see. And in 2 days' time, you will see how you will use Qiskit. So Qiskit is your Python library, and how you see we are all working with Python on Python. We are the teachers from wonderful universities, wonderful colleges and universities, and our students are working in Python. They are taking a part in hackathons, they are taking part in conferences, and they are wonderful students, wonderful mind. The world accepts that Indian brain is the best in the world. So definitely our focus areas now is on the research and innovation. And this innovation word has again come from our Honorable Prime Minister, who says Jai Innovation, who used the slogan just as Jai Jawan, Jai Kisan. The Nara was, the slogan was Jai Innovation. So the part here is the government wants us, the universities wants us to come out of the classroom. The students should come out of the classroom, class studies. They should be developing, innovating something. And this is why you would see even in RKG and different colleges that you are from, KIT, I'm talking about Ghaziabad only. In Delhi, every college has it. So there are incubation centers being set up. There are companies sitting in your own campus. So why are they there? Why are they sitting over there? Why are you giving them a lot of space? This is because we want to collaborate. So the word is collaboration. This is the era of collaboration and collaboration for innovation. So this is where quantum mission of India, national quantum mission is focusing on. Strategic areas are, as you can see on the screen, quantum computing hardware and software, secure quantum communication networks. You have a session here on one of the sessions is on, I think it is day 3. It is quantum teleportation for secure communication. Quantum teleportation for secure communication. This is a topic which will really be talking about Python also. It will be talking about the principles also. So whatever we are looking at theoretically today will be explained and will be done in with programs through the Python framework. So quantum computing hardware and software, secure quantum communication networks, quantum sensing and metrology applications. They are very for oil exploration, it will be very handy. For defense, they will be very handy. Building thematic research hubs across India. So this is one of the mission. So, main objective is building thematic research hubs across the country, and this is what we are doing. India is doing. India, in fact, is giving a very good facility in form of for the government. In fact, is giving virtual labs. So they are giving the virtual lab facility from IITs, Monday, IIT Bombay, and then IISC. Virtual labs are being given free of cost to the colleges and to the universities. We got at Jamia Hamdard, I look at the chat window at the end for the question answers, because when I'm taking the session, I'm unable to see anything over there. So I really apologize. I wouldn't be able to see them. At the end, I'll look into all the questions and try and answer every question in the time frame. So this is how India is really progressing, and this is how we are working ahead. Is investing 6,000 crores of rupees. So you would say, sir, is it only on paper? No, there are leading research institutions. There are a lot more. IIT Mandi, IIT Bombay, they are working and they are giving virtual labs free of cost so that the students can use their expertise. And this is at Jamia Hamdard, we have been using the virtual labs. At Jamia Hamdard, we have got 5G labs free of cost. And if you apply, your college can also get 5G or 6G labs, which will come very shortly. You can get them free of cost. So you just see the kind of efforts being put in by the ministries, being put in by the government, being put in by our country. So leading research institutions, we would find TIFR. So TIFR, I didn't get the full form in the previous slide. So Tata Institute, Fundamental Research, it's in Mumbai. So pioneering quantum computer development and fundamental quantum physics research with world-class scientists. The world-class scientists at the center, TIFR. Then IISc, leading quantum algorithm research and developing practical applications for quantum computing systems. It's not, as I started my slides with, it's no longer, it's a fantasy. It's no longer a film kind of a script. It's really happening. And once it is going to be, we are able to successfully launch it and develop the systems, we will definitely be taking a giant leap in healthcare, in finance, and logistics. So, IISc is one of those leading research institutions. DRDO, we are all knowing about it. DRDO's role in Indian development has been tremendous. DRDO is focusing on quantum technologies for defense applications and national security infrastructure. Just as I was reading, I was going through one of the article from a foreigner, and he said that the day any country would successfully solve the cryptography problem and cybersecurity, they will be a big threat to the defense of any country. They can invade any country through the digital system. So this is how, uh, this is why the research in quantum computing is really going to be very, very important. We have to move ahead. So global partnerships accelerating progress. As I said, you can write your code, and most of you must, they are your professors from wonderful universities, as I said. You must be using Jupyter or Anaconda framework. You must be using Google Colab. If you don't want to download everything, just go to Google Colab and you can run the code that sir will give in Kixit. So the workshop that the professor sir will do, definitely you'll be getting a lot of idea. But from my side, I would say even Google Colab, if you use, you can run your code on that. Cut from one window, just paste it into that Google Colab and execute it. And let me tell you, everything is running. You're able to generate a quantum circuit. You're able to generate a header mode gate. You're able to work on C naught. You're able to work, and you will see immediately, you will see the results. When you see, there will be 50% of the times it will be in zero state, 50% of the time it will be in one state or in between states. uh, Casket, when you will do, definitely will help you a lot in visualizing what we are speaking theoretically today. So a lot of things before signing off today. I'll definitely be talking about Python libraries. I'll be talking about quantum AI frameworks, how we are moving ahead. So we are going to talk about that. And another part, I'll summarize everything that I have taken up. Towards the end, I'll summarize also. So IBM collaboration, IBM is really helping access to IBM's quantum computing platforms and expertise through strategic partnerships with Indian research institutions. AWS integration, we said Cloud One, leveraging Amazon's bracket quantum computing services to enable Indian researchers to experiment with diverse quantum hardware. As I said, if we can use their hardware. Thank you for the coffee. And international research and development, collaborative research programs with leading global universities and quantum technology centers worldwide. These partnerships will provide Indian researchers with cutting edge quantum resources, accelerating algorithm development and practical applications while fostering knowledge exchange. So, the government is working on knowledge exchange so that we can gain from their expertise and they can gain from our intelligent minds. So, this is how the collaboration is going on. So thriving quantum startup ecosystem. There are startups also here, QNU Labs, developing quantum safe encryption and secure communication networks. This is one of the topic you're doing on day two. Developing quantum safe encryption and secure communication networks to protect critical infrastructure from future quantum threats. As I said, threats are going to come at a later stage. Then QPI AI, building scalable quantum computing systems and making quantum technology accessible through cloud-based platforms for enterprises. Then Boson Q PSI, creating quantum simulation software for engineering applications in automotive industry, aerospace, and material science industry. Indian quantum startup landscape is rapidly evolving. We are really working in that direction, attracting significant investment and talent to commercialize breakthrough quantum technologies. Never before there were so many patents and copyrights and design being filed for quantum computing. So there is a time now when everyone wants to learn the most. Our students are really working on that. The researchers are basically working on this, and they're coming out with some good patents on error correction, and they're coming with patents on this one logistics, the route optimization and fuel reduction part of it. So if you talk about startups, QNU Labs, QPI AI, Boson QPSI, they are really helping uh, move us. They're really taking us forward. So groundbreaking quantum communication, if you see, this is one of the word QKD that you'll be discussing in next 4 days, next 5 days. You will again and again be talking about quantum key distribution success. Indian researchers have successfully demonstrated quantum key distribution over 100 kilometers of optical fiber. So we have been able to communicate. This is session number 2 tomorrow, where they are talking about quantum teleportation for secure communication, and they'll be using the Python libraries for that and the code also. So Indian researchers have successfully demonstrated quantum key distribution, QKD, over 100 kilometers of optical fiber, establishing ultra secure communication channels immune to eavesdropping. That means hacksters are being kept away from the malpractices. So quantum satellite mission, as I discussed in the previous slide also, plans are underway to launch India's first quantum communication satellite by 2026 this year, enabling secure space-based quantum networks across the nation. This achievement positions India among an elite group of nations with indigenous quantum communication capabilities critical for securing government, defense, and financial communications. So banking sector, the finance sector, the defense sector, they will all feel secure if we are able to launch that satellite. So it's the work is almost done. It can be launched this year. So what are our Indian ambitious 2026 targets? 50 quantum bit computer. We are looking for 100 qubit quantum computer also. Target to develop and deploy a 50 qubit quantum computing system approaching quantum advantage for specific applications. 2026 expected deployment of quantum satellite and advanced computing infrastructure across the research institutions. A lot of money, as I said, 6,000 crores have already been granted, and every year the money has been transferred for this. There are 100 plus research teams, growing ecosystem of quantum research groups across universities, labs, private sector organizations are also coming forward, startups are coming forward, helping us. So this is how our ambitious targets are. We are also targeting 100 qubit quantum computer very shortly. So what is it that is going to be the real impact of quantum solutions? So healthcare and drug discovery. As I said, healthcare is going to benefit a lot from this these solutions. As I said, this is the time when all universities and colleges, they're really going for these conferences, workshops, and then FDPs and Atal FDPs. It is MMTC is looking after different kinds of FDPs, and they are paying heavily for the conduct of these FDPs. So, what help will it give? Healthcare and drug discovery. Quantum computing will revolutionize molecular simulation. We will be able to do the simulation on a quantum computer, fast accelerating drug discovery and enabling personalized medicine for millions. This is the last word that is here, personalized medicine. So, this is the word which they are, sorry, sorry. Didn't work. So personalized medicine. I'm doing my postdoc and I'm working on personalized medicine, and I'm now working. Already submitted a paper. It's there on internet also, indexed also. The quantum technique for personalized medicine. That means you cannot treat every patient with the same set of medicine. It's like your algorithm should be able to find out personalized medicine. This is where the research is really looking up. And with quantum computers, healthcare and drug discovery is really looking up. My personal experience, as I said, I'm working on this project right now in postdoc. I'm doing it from NTUB, Vietnam. So this is a wonderful opportunity for me also to work on their resources. Then energy optimization, optimizing India's renewable energy grid, improving solar and wind power distribution, discovering new materials for efficient energy storage, better battery storage facilities. So, energy optimization is one thing where quantum is really going to help. We'll talk about it because I have linked this to SDG goals also. Sustainability development goals that UN has set for the entire world. By 2030, everyone has to fulfill those 16, 17 SDG goals. So we'll see how quantum computers can really help us achieving that target also. Then AI and machine learning, as I said, it enhanced quantum algorithms with supercharged AI capabilities. AI is always standing for accuracy. Fine, and the speed will be given by quantum. So quantum AI frameworks, as I'm talking about, you're already working on SVM, CNN, and all. So you see, if we add quantum to it, it becomes QSVM, QNN. So they are really the talk of the hour because our researchers, our students, our scholars are already working on these. So as I said, you can test it on simulation, the results. Even if you don't, you're not satisfied with what simulator is giving you, I said, you can go to the Google Quantum AI Lab. Just go to their site, Google Quantum AI Lab, and you can create your own login with the password. And then you can just submit your research work over there, your programs that you're writing, the output that you want. And finally, when it is complete, processing is complete, you will get the complete solution in your mailbox. So the world is looking up. So Indian quantum future leading the revolution. We are into a, as I said, always India is really on the path of progress. This is really a good work done by the government, good work done by the public. We are all working at the university level and colleges, and we are really working hard. Never before were so many books written on quantum or on artificial intelligence. There were not so many patents or copyrights or trademarks being filed. Now there are the maximum work being done because it's a habit now. It has become a habit. My habit, personal experience is whenever I'm doing something, my students do it, my scholars do it. I get the design for it. I get the utility patent for it, so that it really helps that researcher also, because when he is putting the patent details in his synopsis as well as final thesis, it really helping in evaluation. So, as professors, you can always help your students to develop something good. And as soon as you develop something good, just encourage them to file the design patent for it or the utility patent for it, it will help not only the student, it will help the professor also, it will help the college also, because NIRF ranking, NEC ranking, as we say, and now the ranking system will change with the new adoption of the legislation. You will see, you will get wonderful points every, you get the CAS promotions also. So CAS promotions, if your students are doing good work, if you are publishing SCI papers, Scopus SCI papers, you're getting 20 marks. So by the end of 1 year, you're able to collect 150 to 200 points. By 5 years, you're able to collect 500 to 1000 points and you get the promotion. So this is all leading to your promotions also, your welfare also. So my part here is whenever your student is doing something good and you are doing it, just encourage those people to file it. The colleges are helping to file. The colleges are giving the money for the patents and design to be filed. So why not do it in quantum computing? If you're doing the work, you will start doing it. I'm sure about these, after these 5 days, what will happen? You will really get into Python and you will start working on these algorithms of quantum, because this is a very, let's say, tempting field to, we'll talk about it. So we have about half an hour still there. 35 minutes, we'll have the question answers also, and session also we'll just complete. So India's quantum future innovation hub is one of the prospects we are looking at, establishing India as a global quantum innovation center. We want everyone to know that yes, India wants to work on quantum and India is doing the best. Then problem solving, addressing critical challenges in healthcare, the climate, as we'll just see, how we can use artificial intelligence and quantum computing in climate, because climate change is always a problem. Then our forest areas are being reduced. Look into that also through quantum computing AI framework. We'll discuss in SDG goals. So addressing critical challenges in healthcare, climate, and infrastructure, and global leadership, positioning India as among the top quantum technology nations worldwide. This is, as I said, 2047. We have to be the best, the which grow in the world. So Viksit Bharat, Unnat Bharat, Sabka Saath, Sabka Vikas. All these slogans are really in sync with what we are doing right now. We are working for each other. Second part, I would say, always do the collaboration. Collaboration is the word that is really the need of the hour. Don't stick to your college and your students. Your students can work together in hackathons. You can pick up the students from other college. You can pick up the teachers from other colleges. You say, look, my strength is this. I can develop the algorithm. You do the coding part for me. Pick up some BTech student or a BTech faculty who is good enough in that. So collaboration is always a mantra, which is collaborate with the world. LinkedIn is the best place to do it. Just you see anyone working in quantum or in AI technologies which interests you, just send a message to that person, sir, I want to work under you. A very polite message, sir, I want to work under you. And after, let's say, a few hours or next day, even the best of researchers will get back to you and they'll say, yes, we want you people to work with us. I found my postdoc only on this LinkedIn. So I found my professor, supervisor, co-supervisors from NTUB. I found them through LinkedIn. I said, sir, I want to work on this healthcare, smart healthcare, personalized medicine using quantum. So he said, why not? Just come and work with us. So this is how innovation has to take place. We have to move away from the classroom and then we have to innovate and we have to collaborate. So innovation hub, problem solving, global leadership with strategic investments, world-class research institutions, and a thriving startup ecosystem. India is poised to become a quantum superpower. Definitely, inshallah, one day we'll be becoming the quantum superpower, harnessing this transformative technology to drive economic growth and solve humanity's most pressing challenges. So this is where we have to become the best in the world. So we've already taken about 1 hour. So we have about half an hour to continue with the session and then ask the question answers from you. So application areas of quantum computing, where quantum computing is being used. We already tits and bits. We just talked about it now in detail also. We'll talk about the algorithms also. I talk about Python libraries also. So cryptography and security, Quantum computing is transforming how we think about security and encryption, offering both unprecedented threats and revolutionary protections. So we are under a threat. If someone else gets into quantum and do it before us, they can challenge our system. They can break into our system. So our stress here is we should lead the world. We should be number one here. So breaking classical encryption, this is a very big threat. Quantum algorithms like Shor algorithm, the name came up. So Shor's algorithm, quantum algorithms like Shor's algorithm can crack RSA and other classical encryption methods in minutes, exposing the vulnerabilities in the current security systems. So the algorithm, I'm sure, Cascade, when you'll be doing, we will be developing this Shor's algorithm and the Grover's algorithm. Then second, quantum key distribution, QKD, we talked about it. It creates truly unbreakable encryption by using quantum mechanics principles. Any attempt to intercept the key changes its state, alerting the users instantly. So, this QKD we are already working on. There's a lot of research going on developing this, making it stronger. Then the secure networks, the session is coming tomorrow for you. Building quantum safe communications across networks ensures data protection in banking. The banks were worried about it. Banks were saying, what will happen if our system is just hacked or something wrong takes place? The users will lose the money. The government and healthcare against future quantum threats. So we are working for this secure networks, quantum key distribution, breaking classical encryption, optimization problems. We said we are solving the logistic problems here. Quantum computing excels at solving complex optimization challenges that would take classical computers years to process. These applications span industries from logistics to finance. So, key applications, supply chain, we understand what supply chain is, and route optimization for global logistics. We are all want to do fruitful businesses, want to earn the profits. So, our supply chain has to be the best, it has to be optimized. So, quantum is really going to help in optimizing the supply chain and the route optimization. Even your, let's say, your Google Assistant, when you sit in a car, will guide you. So this is the shortest path. So, and as soon as you start moving after, let's say, 5 minutes, it will immediately say, sir, there is a jam now. You can take the alternative route. So if we apply quantum into that, it will really be even more helpful. We'll just look into it with examples and with the code also. So supply chain, portfolio management, and asset allocation in finance. This is really a very big need of the hour, portfolio management and asset allocation. Energy grid optimization for renewable integration. Government is working on point three, energy grid optimization. So energy grid optimization for renewable integration, because somewhere down the line, our generations are never going to forgive us if we are going to keep using petrol, diesel. So traditional fossil fuel, if we are going to keep on using it, for the future generations, there would be nothing left. So they will never forgive us. So we have to look for alternative source of energy, and this is where SDG goal also says go for wind power energy, go for wind energy, go for your that on your rooftops now you have the solar energy coming up. So every college, university, they're getting points now on using those solar panels. So energy grid optimization, we'll talk about it. Traffic flow management in smart cities. India is looking for 100 smart cities. So 10 to 12 smart cities are still on your tips like Odisha, then your Pune, and then your Lucknow and Jalandhar, Odisha. So there's so many smart cities in India for where we need to have traffic flow management, and this is going to come up with quantum computing. This will get better. This is another session that you have on day 3, quantum teleportation for secure communication and quantum gate based VRP model for communication. So it's really going to be using Python for implementation. And there you'll see the theory that we have done on the first day, the concepts, the principles that we are talking on day 1 are really going to be practically implemented also. So I really congratulate the organizers for coming up with a wonderful schedule of it and the wonderful layout of the sessions. They are on one top of the other. but only after you are understanding something from the previous day. So Cascade Day, please don't miss that. Cascade is really going to give you a lot of advantage because there Cascade is one of the Python libraries. There are other Python libraries also, Cascade, CIRQ, Kirk, then is PennyLane, IBM, Google, TensorFlow, and PyTorch, PyQuil, Project Q. They are all wonderful libraries that really going to help you with quantum computing, programming computing. So portfolio optimization in action, quantum algorithms can analyze thousands of investment scenarios simultaneously. Thousands of investment scenarios simultaneously, balancing risk and more effectively than classical methods that we are using. The data input, historical prices, risk factors, market conditions, then quantum processing, simultaneous evaluation of all possible combinations, and optimal solution, the best risk adjusted portfolio allocation to the customer. So, quantum simulation again is a word. This is going to come up in one of the sessions, definitely. Quantum simulation through Python. So quantum computers can simulate quantum systems naturally, a task nearly impossible for classical computers. This breakthrough accelerates discoveries in chemistry, material science, and drug development. So you say drug discovery is going to really benefit, simulate molecular interactions. We're using simulation word. Find something which is not real but simulated. Simulate molecular interactions to design more effective medications with fewer side effects, reducing development time from years to months. So, if you are going to take it, you are moving from years to months and to days. Material science model atomic level properties to create superconductors, batteries, materials with revolutionary characters. As I said, those who understand physics have done it before. They will really love this quantum mechanics being implemented in the lab using Python. So, drug discovery, material science, complex molecules, understand protein folding and chemical reactions that are too complex for classical systems. So, classical systems are too complex. The word work is too complex for classical systems. So, this quantum computing is going to help you simulate complex molecules. So, somewhere in a session, we'll also be working on that. So, machine learning and AI framework, as I said, we are now working on this. Earlier, we said as SVM, fine. Then we said neural networks. But now we are talking about QSVM, we are talking about QNN, we are talking about quantum and enhanced reinforcement learning and blah, blah. So looking into machine learning and AI, how quantum is benefiting from it. Quantum computing promises to supercharge artificial intelligence by processing vast data sets and recognizing patterns exponentially faster than the classical systems. Quantum speed up, machine learning algorithms run exponentially faster on quantum hardware, processing massive data sets in seconds. If you're not satisfied, as I said, if you're not satisfied with the code that you're writing in Jupyter, Anaconda, or in Google Colab, you can go to Google Quantum AI Lab and you can submit your work over there, the code over there, and execute that. And within, let's say, one day, by one day you will get that, but within few hours you get your output because there is always a queue over there. There's so many people who are there in the queue asking for the resources. So you will get to work on the real supercomputer through this Google Quantum AI Lab. So quantum speed up, machine learning algorithms run exponentially faster on quantum hardware, processing massive data sets in seconds. Pattern recognition is another AI domain. Enhanced clustering and classification for complex data structures and high dimensional spaces. So both clustering and classification, which are the backbone of artificial intelligence in pattern recognition, then get benefited if we are using quantum computing. Quantum neural networks, as I said, QNN, replacing ANN, newest architectures, new architectures that leverage quantum superposition and entanglement. These are the two terms which you will see. Please don't miss out in Cascade when you do it using Python. There you will be writing a code for superposition. You're writing a code for entanglement, just 7, 8, 10 lines of code. And then you will see when you run it, you will feel, yes, The bits are changing from 0 to 1. They are moving in different states. And entanglement also you'll get to see. So real world applications from image recognition to natural language processing, NLP, quantum ML is reshaping AI possibilities. So even NLP is getting uh, a lot of benefit of working with quantum. NLP, we all understand this Alexa. Alexa, what is 2 plus 2? Alexa, open the door. Alexa, close the door. So that will even become more efficient. So chemistry and material design, we say the chemistry solutions, the physical solutions, the revolutionary capabilities. Quantum computers can simulate chemical reactions at the atomic level. You talk about electrons and protons, revealing pathways and properties impossible to observe classically. Catalyst discovery, design efficient catalysts for clean energy and industrial processes. New materials can be found, create new substances with custom properties, stronger, lighter, and more conductive. Environmental solutions develop carbon capture materials and sustainable alternatives. So there's so many things. I'll just talk about the research options that you can have. Then the finance and risk analysis, as we said, portfolio optimization, quantum algorithms identify optimal asset allocations across thousands of securities while managing complex constraints and correlations. Then fraud detection, pattern recognition at the quantum speed, spots anomalies in real time, protecting against sophisticated financial crimes and cyber threats. Now you see, immediately the system will get to know one of my check bounced in, let's say, 10 years back, and they still my history is very bad with the bank. So this is the use of artificial intelligence, and now with quantum computing, they exactly know your data. So derivative pricing, Monte Carlo simulations run exponentially faster, enabling more accurate pricing of complex financial instruments and risk assessment. This Monte Carlo simulation will be done in Qiskit also. So Shor's algorithm, Grover's algorithm, and this Monte Carlo, they will be something to look for when you are doing your Qiskit session on day 3. This is really going to help. So industry, I see a lot of messages now, 48 in fact. So I look into them after 10 minutes. I look into them also. I'll come face to face also. So just pardon me. Let me just continue. The numbers increasing because it's the time where we have to close also. It's a dinner time also. So just bear with me for 10-15 minutes, and then we'll have the question answer session. And then you'll have your feedback session. Sorry, your attendance system. So industry impact by the numbers, market value by 2030, $125 billion, then faster drug discovery by 40% faster, optimization improvement 10 times, annual investment $850 million. So this is really going to help us. Quantum future is really awaiting us. Now, this is the part which is very important where the government wants us to talk to you with reference to quantum computing. This is, I have gone to different workshops and conducted, and they want the people to be aware about sustainable development, SDG, because UN goals, 16, 17 goals that you have, they have to be fulfilled by 2030. So 2030, then Corona was in between over there. The Corona ate up 3-4 years. So we are still rushing to complete those sustainability goals, whether it's in education or it's in healthcare. So the government really wants to focus on this aspect. So 4 critical SDG focus areas, where SDG 3, Sustainability Development Goal 3, good health. So revolutionizing drug discovery through molecular simulation and enabling personalized medicine at unprecedented scales. So this is where last let's say 1 hour, 10 minutes we have been talking. So quantum computing is really going to help. It's really helping. It's really going to help in future also, revolutionizing drug discovery through molecular simulation and enabling personalized medicine. This personalized medicine is a very important term. As I said, my research and postdoc also focusing on personalized medicine, where we should also be able to, let's say, deliver personalized medicine at the doorstep. This has been one of my designs that I have done in the utility patent, also filed for it. So good health. Then SDG 7, again, goal 7 is very important. And this is where the entire existence of a country is basically focusing on clean energy, optimizing energy grids, and accelerating the development of next generation battery materials for renewable power. So you see, you have those solar panels on top of your building, and the batteries are different to store the power. So we are looking at next generation battery materials. So this is where quantum computing can really help us to find out the material which is suitable. Then optimizing energy grids. Now these energy grids, now you see, earlier when, let's say 10 years, 15 years back, there were electric cuts. There were long electricity cuts. But now you see those electricity cuts have been reduced to, let's say, negligible part in metro cities and big cities. In villages, still it's because they have to give electricity for farming also. So that may be a problem. But then here, energy grids are working, and we are looking at optimizing the energy grid. So everyone should be getting the equal, let's say, the equal weightage. So clean energy is one of those sustainable development goals the government is really serious about, right from your on your roof. Now, even the universities, colleges, they're given the knack points. If they are making use of those solar panels, then there is the wind energy. You can do it. Move away from the fossil fuel. That's the need of the hour. That's what the government is saying. Then SDG 9 is industry innovation. We just said transforming material science with quantum simulations that unlock sustainable industrial processes and infrastructure. So we are looking for innovation, and innovation that will take our country to a path of, let's say, development where we are number one in the world. So industry innovation, as I said, now there are different colleges, different universities which are having incubation centers inside the campus. And initiative is really, let's say, it's a breakthrough. The organizations are sitting in your campus, they are interacting with your students. The students are coming up with the research idea, and they're giving the research idea to that industry. So they are developing the solutions, they are helping the college in developing solutions, they are helping colleges in getting the knowledge transfer. So it's a long way. So good health, clean energy, industry innovation, climate action is another. SDG 13 is very important. And this is where I think we all have to look into climate action, enhancing climate modeling accuracy, and optimizing mitigation strategies through quantum powered computation. Climate is something which is very important. You say there are pollution issues, there are other issues, there's a climate warming uh, issue that is going up. So if you want the future generations not to curse us, not to say, what have you done for us? They will never forgive us if we are not going to take these actions for the future. Good health, clean energy, education for all is another very important development goal. Education for all, right here sitting in India, we can have it. Anyone sitting in Nigeria can have it. Anyone sitting in, let's say, Myanmar or any other country in the world, it's America, UK. Now, the best part here is we are all connected. And during Corona has taught us one thing, to be computer savvy, to be using these computer resources at our best. At our best. We are the best in using them. Definitely. We are using Zoom, we are using Google Meet, we are using other options. We are developing our own LMS and then having it done. So colleges, universities are really working hard to get things done. So four critical SDG focus areas. So quantum breakthroughs in healthcare, as I said, simulate protein folding in hours instead of years. Molecular interaction, model molecular interactions for target drug design, predict patient-specific treatment outcomes, reduce pharmaceutical development cost by 40%. There's always a ad coming up of Anupam Kher, and he's saying, I have met IIT people, and They have explained me how the cost of your medicine will reduce to just 2000 instead of 6000 a month that you are doing it. So things are happening and they are transforming the medical science if we are using this approach. So powering the clean energy revolution, as I said, grid optimization is very important. Quantum algorithms will balance the supply and demand across complex renewable energy networks in real time. Everything is happening in real time. So battery innovation simulate new materials at the quantum level to create batteries with 3 times capacity and faster charging. If we have seen our batteries, they take 7 to 8 hours of charging, but there are batteries coming up, your mobile batteries are coming up, instantly they're getting charged up. So battery innovation is one field where they are really working on maximum efficiency, reduce energy waste. This is important. Reducing the energy waste by up to 30% through quantum enhanced distribution and storage systems. So this is, yeah, waste management, water management, everything has to be looked into with efficiency. Um, am I audible and visible both? There's someone on the mic drawing on the
Yes,
screen.
sir.
Please 5 more minutes. Don't draw on the screen. It will go on the recording part. Please rub it. So climate modeling at quantum scale simulate complex solutions, optimize mitigation strategies, enhance predictions. So climate, again, climate modeling will benefit a country a lot. So quantum impact by the numbers, we see there are 58 messages now. I'm just finishing in 5 minutes. Just give me 5 minutes. Faster drug discovery, reduction in time to identify viable pharmaceutical candidates, 30% energy grid efficiency, 10 times climate model resolution, projected economic value is there. So we are moving in numbers. So innovative opportunities, quantum algorithms for sustainability. This is where I said our research scholars are really working on developing specialized algorithms that solve optimization problems in carbon capture. This is one of the research areas where it is getting published also in SCI papers. Water purification. I have got one Saudi Arab project on water purification and sustainable agriculture. So these are the research areas where we are looking, our candidates are working on sustainable agriculture also. Quantum inspired classical solutions apply quantum principles to enhance existing classical computing approaches, delivering immediate sustainability benefits. As I said, a lot of people are working on this variational quantum eigensolver, which is a hybrid quantum classical algorithm. Then cross-sector collaboration unite academia, industry, and governments to scale quantum solutions and maximize real-world SDG impact. This is what the government is doing, bringing the academia, the industry, and government is coming together to find innovative solutions. So navigating key challenges, we are moving ahead. Technical barriers, bridging the gap between quantum theory and practical SDG applications. As I said, we are organizing these workshops basically to remove those technical barriers, bridging the gap, scaling quantum solutions, human capital, building a quantum ready workforce across disciplines, training sustainability experts in quantum fundamentals, creating educational pathways for emerging careers. Then there is global cooperation, as I said, establishing international standards for quantum sustainability research, ensuring equitable access to quantum computing resources worldwide. This is, I said, Google Quantum AI Lab. You can upload your program over there if you're not happy with the simulation software. So, this would be the last slide. Definitely, then I'll come face to face. 2025 to 27, this is for this SDG, this is the foundation phase. Demonstrate quantum advantage in specific sustainability use cases, launch pilot programs for healthcare and energy applications. 28 to 2030, scaling phase, deploy quantum solutions at commercial scale, integrate quantum computing into climate modeling frameworks globally. Then 2031 to 35, transformation phase, achieve measurable something which you can measure SDG progress through quantum innovations, establish quantum computing as essential sustainability infrastructure. So join the quantum and sustainability revolution, take the action now, build a capacity, develop quantum literacy across the sectors. This is what the government is doing. collaborate globally, as I said, share your knowledge, resources, and innovation across borders. You should not shy away if you are using anyone on LinkedIn, meeting anyone on LinkedIn, just send them a message. Sir, I want to learn from you. I want to work under you. Your work is tremendous. And you say, immediately you will get the responses from them. So this would be the last slide, promise. Just 3 more minutes and then I'll come to face with you for 5 minutes. So these are the friendly books that I read recently. They are available on internet in PDF format also. Quantum Computing for Everyone by Chris Banhart. Learn Quantum Computing with Python and QHash by Sarah and C. Kaser and Cassandra. This is a wonderful book if you wish to be working in programming. It covers Qiskit also. Introduction to Quantum Computing by Ray Lapierre covers basic and application. This is a very basic book, the third one. You can always look into it. The PDFs are available on the internet, fine. Advanced books, they are not available online, but in your libraries and all, you can always order because the colleges, universities will always send a format to you. Which books do you want to order for the year? And you can always enter these kind of a books, quantum computation and quantum information. This is one of the session that you have on information by Michael Nielsen. Quantum Computing Principles and Paradigms, edited by Rajkumar Boya. This is one of the best books I have read. They've edited this book, right? Sukhpal Singh Gill, but this is one of the best books available. Quantum Computing Principles and Paradigms. Just mind you, we will have to really study this and to get into the groove of this, to get into the skin of this topic. This is really interesting because you are able to, the last two, Quantum Computing by Practice, Hands-on Quantum Computing with Python by James Weaver. So you'll be having this session passed on. You will be having the slides. You'll be having the video of it at a later stage, but I'll pass on the PPT also so that you can go through these books if you wish, because our basic day three would be the most interesting part of this FDP, where we are working on hands-on quantum computing with Python through Qiskit. So Qiskit, again, I said, is really going to help you out. Is Qiskit just with 3 lines of code from Qiskit import quantum circuit. This is we have been doing in Python. From Qiskit import quantum circuit, the QC is equal to quantum circuit with 2 gates, and then call the header merge gate, and then call the C naught gate. And you see when you run it, you will see on day three, once you run it, you will see a quantum circuit on the screen. Instead of this English kind of thing, you will have the circuit onto your window. So summarizing everything that we did, we said Python libraries will be very interesting when you see Qiskit. Quantum AI frameworks are really getting a lot of importance because we are working on SVM already. We can convert into QSVM. We are working on artificial neural networks. We can convert to quantum neural networks, quantum enhanced reinforcement learning, which will help us in healthcare, finance, logistic, route optimization, smart city solutions, error correction. So one of the session also focuses on error correction. So please do it quite cautiously. So I think this should be my uh, slide end. Though I had one more presentation with me in case I finish earlier, I'll take it. But I think this is all. It's 5 minutes left. I'm just stopping the sharing part now. That I can come to face with you. Virendra sir, Virendra Saraswat sir, namaskar.
Good evening, sir. Good evening, sir.
Wonderful to see you on the screen.
Thank you so much, sir.
सर दिन बन गया और बहुत दिन से मुलाकात नहीं हुई थी.
नहीं. Thank you
Wonderful
so
to
much,
see
sir.
people from
Same here.
RKG. Amit Singhal sir and everyone, Pawan Kumar sir. It's always a wonderful feeling. It's my second home basically. In Ghaziabad, if I say my second home, my second home is basically RKG. So I've been coming for conferences, for FDPs, everything I'm coming here. So this is a wonderful college I've been seeing since 2000, really working and getting into the NAC A++
No doubt,
kind
sir.
of Yeah, wonderful thing. So
Yeah.
thank you from
And
my side. If there are any question there, I can see the chat window now.
no question, sir, from my side. This is very really useful and informative session.
Thank you, sir. So we are all
LinkedIn,
learning.
the LinkedIn,
So
sir.
yes.
Share
Hello.
your LinkedIn.
LinkedIn, my Dr. Ehtaram Raza Khan, the same name that you will see on the poster.
Actually, sir name is sorry to interrupt, sir. Sir name is very famous. You can write in Google Dr. Etram Raja Khan, and now you will receive each and everything, sir. No, sir, thank you.
So, sir, you'll see a lot of programs on Doordarshan also.
Yeah,
So the
yeah.
audience and they can always look into two programs on deepfake and digital hygiene and this blockchain and quantum. They're on Doordarshan itself. So I've been lucky enough to have wonderful friends like Saraswat sir, Amit Singhal sir, who have always inspired. I worked for IMR for 5 years, and then I went to Jamia Ahmedabad. So this place is a wonderful city, is a wonderful city, and we are growing with each other each day. Saraswat sir has been working on very good projects recently. He's not telling about his expertise, but I think he's a wonderful professor with wonderful books and wonderful presentations that I see all over. And sir, your look is totally different. It's hairstyle is really gone a sea change.
Thank you, sir. Thank you.
So please don't mind, but it's just a compliment. You're looking really
No, no,
smart,
no,
sir.
sir. It's okay, sir. Thank you.
Thank you so
So
much, sir,
thank you, sir.
for the highly
Thank you, sir, for
informative and
the
inspiring
highly
session.
informative and inspiring session.
Sir, if we can have one pic together, कभी कभी मौका मिलता है, if we can have one pic,
Yeah, sure, sir.
जो आप लोग लेके मुझे भेज देना. Thank you so much,
Pawan,
sir.
sir, please. पवन सर पिक हो गया क्या?
Yes, yes.
Okay, sir. धन्यवाद.
Okay, thank you, sir. Thank you.
Thank you
धन्यवाद
so
सर,
much, sir.
धन्यवाद.
Thank you, sir.
कनिका मैडम लीव करें?
Yes, sir. Just kindly ensure that you have submitted the feedback form that has been given.
Okay, ma'am. Done, ma'am.
Done, madam.
With this, we conclude day one of the Atal FDP. We look forward to your enthusiastic participation in the upcoming sessions. Thank you all and have a pleasant evening.
Thank you,
Thank you
ma'am.
so much.
Welcome.
Thank you so much, sir.
Thank you, sir. Thank you.
Ma'am, I filled already one link, whatever shared earlier. So again, the link will be shared or the same link you are talking about?
Sir, Pawan sir has shared the link in the chat section.
Just now, again, the next one?
Yes, he has
New one.
sent this
Okay.
again.
Oh, okay, ma'am. Okay, ma'am. Thank you. I'll fill that. Yeah.
Thank you, sir.